Yet. All right, welcome everybody to Dallas Personal Robotics Group. This is our regular monthly meeting. This month we have 2 simulations for the price of 1 entry ticket, and they're on ColleliaSim to model a physical robot, and the line following simulation environment, which DPRG will be using for a contest this fall, thanks courtesy to Ron Grant. My name's Carl Ott, current president of the club. And what we're going to do first is start off with an update by Ron. He has about 10 minutes of presentation stuff. We'll give him maybe 10 minutes of Q&A, and then cut over at about 1:30, half of the hour, to Chris for the main presentation. So with that, I'm going to pause this machine and hand control over to Ron Grant, and off we go.
Okay, great. Okay, let me go ahead. I'll see if I can grab this window. And okay, great. So I've just recently released, as of about 30 minutes ago, I call it version 1.3. Sorry, I think I'm a little bit out of sync with Doug, of the LFS library. So that's available on GitHub, and it's at rongrant/LFS. And what it is a processing library designed to help build a line following simulator, or it's a tool for doing such. Anyway, what I have today is just a few minutes to cover a few updates that I've made in this version 1.3. And let's go ahead and look at the visual run of the program. And let's see, this is what is known as the simple bot. So this is a very simple robot. And what you see that's new are these little purple circles. And when we click on the robot and move it to a given start position, let's say we're looking at this feature here, what we can do is rotate our robot to our desired orientation and then press the M key, and that sets up a marker. And the cool thing about that is that any time then, regardless of where the robot is oriented, if we click on that marker, it remembers where the position is, which is obvious from the circle, but also the heading, so that then we could start running the robot at that point. For example, here we go. So that's that. And these markers are remembered by the application, and there's just been a few changes to implement those in the application that you're using. And there's different ways to handle it. If you've done a development work with the program, then you may want to read up on what's changed, or make a decision on how you would want to probably carry your controller code over to the new framework or the new application. So anyway, so this is also labeled SimpleBot 3, which makes it obvious what it is. Also, another improvement I've made is I now display the sensor information in both the raw sensor data window and also the what I call the robot view. And the robot view is used when we're displaying also the course. In fact, here just for fun, I'll interrupt myself and I'll start up my application that is, or let's start up Will's. I'm going to launch Will's trike demo that I added the enhancements to. And the only thing about it is the spots are not scaled properly in the robot view, so that's something I do need to fix. But here we're looking at his definition of sensors, and the cool thing is, as I move the mouse cursor over the sensor, it indicates what the current level, it's sitting over the logo. Maybe we should move, hang on, let me move it on top of something more reasonable. Here we go. Now, if we tab back, so as we look at these sensors, for example, that sensor is seeing white, and that sensor is seeing pure black, and that sensor is partially overlapping black and white. So anyway, again, at the bottom, you can see the sensor identified by name. You could also rename it if you like, but I've used a facility called Java Reflection that allows me to fish the names that you defined for your sensors and access that directly. So that's a kind of a neat thing. It's sort of automated. You don't have to manually set up these labels for these sensors. So that's that. The one thing, though, is in this case, if we drag the robot around, the controller needs to be active for the sensors to read. Now, I may change that in the future, but for example, if I say G for go, And now I can actually take, well, but we can stop the robot. So, but the controller is still active in this case. So we're preventing the robot from moving. But if you had explicit movement instructions, that might be difficult. But the other thing we could do, hang on as I think about it, is if I put Will's robot back in motion, I could also slow the step rate down, or in fact, I'm pressing, let's say I'm pressing like 9, 8. If I press 0, I freeze it. And now I'm in single step mode. So I could position his robot here and then single step it with the space bar. And now we're moving 1 increment at a time. Now for Will's robot, I did increase the delta for the simulation. I'm running a 20th of a second on his simulation. And one thing you'll notice, I'll go into contest run mode, pressing R. And you'll notice his robot looks pretty nimble, which it is. But if you look over at the real time reading, time is running very fast. Well, that's because in my case, at the moment, I'm running somewhere around close to 80 frames a second, even with the screencast, typically more like 90 to 100. So I'm running his robot about 5 times normal speed. Hence, it's nice that we can speed time up or see the robot run very fast, and but we can also slow it down to near real time. So that's that. So anyway, so that is the new enhancements for the simulation. And again, the main tab is fairly modified. So you would want to replace that. But as far as your code in the controller section, that remains identical, except if you want to update the sensors on screen, it's up to you to color those sensors. So without doing that, the sensors would remain in like as in the past, just as a static field showing you where they are. So this is really completely optional for you to color the sensors, but in a way it kind of helps to produce feedback as far as seeing where the sensors or what your code is doing with the sensors, if that makes any sense. And let me think. I think that's about it. Go ahead.
You were saying that the sensor data is being shown. I didn't see where that was coming up on your screen.
Oh, let's try again. Okay, let's look at this. Okay, so if we look, this is just as we hover over the sensor bar. If you look down at the bottom of the robot view there, you see the line sensor called sensor 1. That's what this line is. So we can see the different elements and what values are being read at that moment. Does that make sense? Let me go to the larger view. So here, element 25, do you see that at the bottom?
Ron, can you move your arrow around the area where the values show?
Oh, down in this area right here. Are they not showing up?
Well, they do show up when you hover over the display. But
yeah, okay, that's the idea. Okay,
yeah.
So in other words, yeah, it's a hover and read sort of thing. So it's just a diagnostic to identify what the sensor is, but not give numerical values for every sensor as the robot's running. But I suppose you could leave your mouse on that position, and if we ran the robot, I suppose we would see, you know, what value is being read by the sensor there at a given time. So it's 1, and of course it's crossing over the line occasionally. So there, that's that. So any questions, I guess? I think that's pretty much what I have to present, and I did not do what I said I was going to do, which is a YouTube video on installing processing and the library, but I'll do that. But I think most anybody who's got the savvy to write a controller is going to probably certainly know how to download processing and the library, but I'll do it anyway.
Okay, hey Ron?
Yes.
You go over what is in, so these are the files that are available to the user, and he has to pretty much configure them. Can you just go over what each file does and hold?
Oh, as far as like within the SimpleBot sketch?
Yeah, now that's the algorithm, I believe, isn't it?
Yeah, well, so yeah, so the main tab is code that you probably will not mess with. So so now if you've already started to play with writing a controller, probably what you'd want to do is import, well, you'd probably want to import the SimpleBot sketch and then drop your code, your controller code, into it, because there's some different, so this tab right here is your controller. So in this case, it's a fairly simple controller. You read a line sensor, which is basically an array of values. In this case, it's like 65 floats. And in this case, we are passing that to a method that we wrote that will calculate the centroid of data within that array. And then ultimately, all we're really doing here is we're coming up with an error term. And then somewhere down here, let's see if I can find it, we are, yeah, let's see, wait a sec, I'm having a little trouble. Controller update, 1 sec. We're coloring the sensor. Then, oh yeah, then at the bottom here, we're actually running a PD controller. So we have a proportional error here to set the turn rate, and then we have a differential error here for the D term. So that's setting our turn rate. And then here we do have a variable target speed, but we could actually make it a fixed target speed by commenting that out. That's, you know, not necessarily a feature you need, but just for fun, I threw it in there. So anyway, so that is your code, basically, is the user controller. Then under user draw, this is fully optional. You do need to have this method, but in this case, you can draw things within the robot coordinate system, and those are just in this case, the outline of the robot that shows up. But again, it's not needed for the simulation. So user draw could be empty. It does get called from the main tab of the sketch, but that's your user code. So we're drawing a few circles. Then we have another panel here, and this is mainly for drawing status information. I hope to improve this a little bit. Mainly, I consider this user code, but this is information related to status, maybe state information, and so forth. So that's called one time every time the simulation takes a step.
So if you, Ron,
yes.
So if this is where if you wanted to capture a run and send it to a CSV file, you would essentially open a file and stick it in here somewhere, and as it went through, it would record that data, right?
Yes, yeah, that certainly. You could come into your user controller, and when you calculate your, let's say, your turn rate and turn speed, maybe just assign this stuff to a variable. At this point, you could write a value out to a CSV file, for sure. That might be an interesting thing to make available to people who want to use other tools to analyze the data. But then, so just to continue on with the other tabs, the user init tab, again, is the place where we define our sensors. And in this case, we define our sensors. We do set up our name and the robot name for contest purposes. We say what course we're going to use. This demo actually allows selecting one of 2 courses. Then we set our acceleration rates, and subject to simulator maximums, which would be a nice thing for me to make a little plainer in the run of the simulation. And then finally, we create our sensor instances. So these are positioned in robot coordinates, and this is explained in the user manual. So we do these in this case, we're creating 3 spot sensors and 1 line sensor. And then we're modifying the 1 line sensor into a half circle. Then we also have a rotation facility, which I'm not using in this demo. Then finally, we can name our sensors for that hover feature using this function, which so far I haven't figured out how to incorporate that into the library. It may not be possible because it uses a special Java facility, and anyway. So for right now, it's incorporated into the main tab of the program. But then there's a new method here called marker setup, and this actually loads the marker. So if we stop this sketch and restart it, our markers are still there from the last run. So then the next tab is key presses, and also a new feature is mouse clicked. And the only thing I have going on in mouse clicked is we hand off the click event to LFS for the purpose of determining if a marker has been clicked on. But otherwise, and if that's the case, we return, but otherwise user could have other mouse click things happening. Again, you may not need to mess with this, but it does need to be present, and there might be a cleaner way for me to handle that, but that's how it's handled now. Then in key pressed, every time you press a key, we upshift the case here, and then here's our keys, and here's a new one. If key is M, we need to call LFS marker add remove. That's what gives us the ability to have those little circles appear. And so really nothing else has changed in the user key tab. There's keys to do things like change speed when you're manually driving the robot, so forth. So that's the end of that tab. Then finally, user reset and run. This tab typically calls the user init method. And then something that's kind of new is we move to start location and heading. And what this allows us to do is if we have set a marker and clicked on it, it's going to jump to that position when we start our robot. So that's something new in the user reset and run. And then in this case, I did set a target speed, but within my robot controller, it immediately overwrites the speed. Unless I comment it out, then the robot will start with 6 and continue with 6. And in that case, if we're not updating target speed every simulation step, we could use the keyboard to vary it. In fact, I could demo that, but let's cut that short. So for this, also our state information, which is very simple in this controller, is only this eprev, which is the error previous for the decalculation in the PD controller. And other than that, that's it. So there is a bunch of junk that goes in this tab, but the rest is mainly your stuff. And I hope in the future maybe to make it even clearer or cleaner. But that's LFS. And
So Ron, if I can summarize what I think I heard,
okay,
it sounds like all of the things that make the environment run are in a library, and in a way they're hidden at this level because there's no need to get into that.
right. And
Okay.
there's nothing from stopping you. The other thing is the process of developing library code is somewhat involved, and that requires using Eclipse. But I can say, and maybe I'll publish something on this, that let me just bring up the library real quick. How am I doing on time?
We're getting tight, but I was going to say because I think at this point this is so rich. It seems to me that first we got to get people involved with controllers, and then for those that really want to go above and beyond, they might want to dig into the library.
Yeah,
Right.
From how to submit robots, it seems. I just want to confirm what I understand. So you've intended that these 7 files are basically user files. These are for the things that vary from one competitor to another. These are the files we would edit. And if you want to have a different platform, so different arrangement of sensors and whatever, that would go into the user init. And if you wanted to look differently, like not like have 2 wheels with a roller, but some other different kind of appearance as it rolls around the course, that you would adjust in user draw.
Correct.
Yep. And then the controller goes in that 3rd file so that the logic of how it interprets the sensors on each turn of the simulator, all that logic would normally go in this user control.
Yes, that's correct. And that's the one that the goal is that, if I make any changes, I fiddled around a little bit, although it shouldn't change much at all now. I mean, I think it's pretty stable, but overall, your controller code is, isn't going to change. And really, I'd say I think I can stay out of just about anything now. I'd be really surprised if anything would change. So in fact, maybe I should commit to that, really. Let's say that
I mean, the simulator is pretty stable. You haven't changed the API to the simulator in a big way in a while. So
right.
And that's where if we get contestants to use Git, where they clone instead of just download, then it becomes much easier to track your library changes against our controller changes.
If we have a competition, you're going to have things like the user interface is going to be same for everybody. Otherwise, what I'm saying is you can't have somebody changing the button, so F is now something else. And it's not clear how this is going to be packaged for a competitor so that a judge can run the program. I mean, these are things to look at. I love the way Ron's done it because it gives you a lot of flexibility.
Oh, yeah.
But what I'm saying is when we go into a competition, you're probably only going to have to be able to change 3 of these files.
That's probably right. Yeah, I think we maybe work on that. Let's give that some thought. But that's probably correct. And
Okay.
I think it should be able to be at the moment run by the contestant, sort of thing.
No, for development and where we are with people, trying to learn how to use it and everything, I think this is great. Okay. But I'm just saying that in the competition, we have to minimize
Variability of sorts.
variability between.
Yeah, right. Some of that is done by the formatting, because really the way it works right now is, of course, when we run the robot. Let's see if we show the sketch folder real quick here. Let's see. So when we run the robot, our runs are recorded, in a I guess it's a CDF file, and a picture is taken of the contest. So if we, in fact, here, let me load let's see.
We're getting a little low in time, but
Okay.
I was going to suggest we could work on these, but I think that, like, as a part of the rules, Doug, as we get closer to this, it seems to me that we should say a minimum competition robot file respects R, S, and space, and the maneuver buttons, so we can define the controls, the standard controls which it has to respect.
Right. Well,
And Ron wouldn't have to code that, right? If we put it in the rule.
Hang on one second. Right now, the way it's set up is it really doesn't matter as long as you can run your robot. But yeah, we could say that. Leave it alone, so that right now we have a run, which I pressed R to run this, and let's say this is where I stopped. Then I can press F, and when I press F, a snapshot of this has been taken, and the data has been written out to a CDF file. So, unless somebody wants to tamper with it, it's pretty good to go. In other words, so if we look at our sketch folder now, if I'm looking at the correct, that's SimpleBot, sorry. Well, anyway, okay, here's RonBot. So if we look at our sketch folder, here we can see snapshots of different runs. But if we go into our data folder, then we would have access to this information and be able to see, okay, here's Ron bot, and I ran for whatever 56 seconds or whatever it was. So, oops, I didn't show.
One last question.
Okay.
I still don't understand quite what the markers are.
Oh, the markers allow you. It's a diagnostic tool, really, that allows you to set up. Usually I've had trouble spots when I try to run the contest. So in other words, if I have a trouble spot before this gap, then I might set a marker here. Or if I have a trouble spot here before the acute angle, I'll drop a marker there. And the cool thing then is I can go here to test that feature, or I can jump here to test that. And I don't have to screw around with the heading and all that. Then I can say run, or go from there.
I have a question. It's more rules related than simulator related. So, are there any requirements to closely follow the line, or are the rules taking into account how well a given robot follows the line, right? Because in me playing with my simulator setup and my simulated 3Pi, I found that at times it just gets lucky. It just goes straight and finds the line again, and you didn't have to take the detour, right? And so, how do the rules account for that?
The
Judge discretion.
Chris, the rules say that you have to follow the line. So, like, if there is an S curve, and you shoot straight across it, that's bad. If you have a stain and you follow the outside outline of the stain, that's bad. Okay, so that's you have to follow the line. Now, does that mean that you have to be exactly on the line? No. I mean, like, I think Ron shows some cutting the corners on the 90 degrees. A lot of robots will go overshoot the 90 degrees and go to the outside and kind of ring on it. Either one of those would be acceptable because you're following the line. But if the line does an S and you go straight, you're not following the line. Now, do you have to exactly follow the S? No, but you should at least wiggle, you know? I think the biggest one is the stains, because the stains are really one of the hardest features on the course. The other one probably is the acute angle. And the acute angle, we've had people undershoot it, people overshoot it, but essentially they're following the line. Okay, so that's fine. Okay.
So Chris, I think you could ask Kareem some Tuesday night, but if I heard him correctly, you know, on his robot that runs around the field to draw his letters out, I think he was doing something as sophisticated as a RMS deviation over the run, you know. But, and I'm not suggesting this to Ron, but I'm just saying I think I've heard Kareem do that. Thankfully, those aren't yet written into our rules. We have enough challenge getting people to make robots in the first place. But anyhow, I'll just throw that out there as
Carl, that's a great idea. I'll write that down.
Oh, I missed. Sorry, of course, I dropped off for about 2
That's good. That's much better.
Anyway,
You don't want to hear that one. It's more software.
Okay. Yeah, I'm pretty well fed up, and I think I'm feeling like I've got the thing in a good enough place that, and it's usable. I mean, I'm able to. You know, I was bragging about running the course, and I probably can, but I'll say that I have areas for improvement, big time. But I have promised I haven't been able to work on my controller when I'm writing other code.
It is well above and beyond usable, Ron. You got to get on your own controller.
Okay.
You just got to park the environment. The gauntlet is down. The code is out there.
Okay.
Contest coming is for those of you watching this video, you can check the associated chat transcript, but there are links to the GitHub repo. We have a contest coming targeted for the December the 12th, a virtual contest this year. And encourage anybody who's interested to clone. Don't download. Force yourself to clone. Learn Git and start to make your controller, and let's go all the way in December. Meanwhile, a big applause. Thank you, Ron.
Great, thanks. Thank you. Oh, deafening. My gosh, wait, I got to turn my speaker down. Okay, speaking of that, I should probably now mute myself. So, Chris, gosh, I've got some time. Okay, get rid of me.
All right. Okay, thanks again, Ron. And so, Chris, guest from way up northeast, we very much appreciate you becoming a regular and jumping on and offering to present. So in the second part of our simulator Saturday, Chris would like to let you take it away with a different simulation environment.
All right, very good. Thank you. So I hope you all can hear me. I see most of you. David Anderson, I see you're on. I see the ceiling or the floor or something. And if I get into code and things and you can't read the font, just feel free to change the layout. That's what I find myself doing. I can't read stuff. So let me switch over to presentation. I have a couple slides to kind of keep me organized. And then we are going to look at bits and pieces of code as well. Let's see. Are you able to see my presentation in full screen mode? Very good. Okay, so this is about ColleliaSim, which is an off-the-shelf sort of open source type / partly commercial robot simulator that I've been using. And I've been using it not just for simulation, but in conjunction with a physical robot, right? And so we'll talk a lot about, okay, how do I do both? How do I do simulation, but at the same time, I build a physical robot? There are a couple links at the bottom here. My stuff is in GitHub, a couple YouTube. There's a YouTube playlist with some videos there as well, if you're interested. Let's see. Now, why am I doing simulation? And I'll have another slide to we can discuss a few other good reasons to do it. But to me, it really boils down to, I wanted to spend less time, debugging the robot. and in particular, as I prepare, let's say, for the annual Trinity College Firefighting Home Robot Contest. It's a contest that's been around for 20 plus years. I think I've mentioned that. I'm in the Hartford, Connecticut area, and that's where the contest is getting run every year, except, well, this year. It's an international contest. You know, it's getting a little long in the tooth, but it's very exciting. Lots of international participation. You know, they have been changing the rules, you know, a little bit from year to year. You know, again, many of you are probably familiar with this and with this basic arena setup in the center here. You've got hallways, you've got rooms. There's a candle somewhere. You gotta extinguish that fire. Okay, that's the main mission. Now, okay, so they have now come up with the, you know, increased levels of sophistication. If your robot's really good and sophisticated, you can operate what they call it level 3. You got 2 arenas, you know, back to back. You know, it involves rescuing the baby, picking it up, you know, delivering it somewhere. You know, it gets, well, you know, they've made it harder and harder. As I'll mention on another slide, I don't really get into manipulators and grippers and arms, so that's really not my thing. Mechanical stuff is not my thing, so I don't really get there. But the point is, I mean, this is an evolving contest, and you know what I like about contests, as much as they get old after some time, right? It gives you a specific goal, a specific mission, right? You kind of know when your robot's done. Otherwise, you just there's open-ended tinkering, which is fun, of course. But it's good, I think, to have a specific task in mind that you want your robot to execute. Okay, it just gives you focus. So this is what gives me focus every year. I mean, I'm not every year, and I might be participating a couple years in a row, and then again take a 5-year break, that sort of thing. So that's my motivation, right? It's a simple task, or seemingly a simple task. You know, you navigate and blow out this candle. But as all of you know, I mean, the devil's in the detail. You know, if you want to make sure you don't get hung up on these, you know, corners, etc., it takes a lot of hard work and a lot of debugging to get this really to work reliably. And I just wanted to find a way to be more efficient at doing that. Right? It's hard as it is. You know, I want to make it a little easier. Okay. Now, apart from that firefighting robot, which actually had to mostly disassemble for parts, you can see it's the mechanics of it. It's not very sophisticated. You know, again, mechanical stuff is not my thing, but it's got a lot going on in terms of sensors and motors. Because it's got a fair amount of stuff going on, I will, in this presentation, actually use a 3Pi as a sample simulated robot. So we'll talk quite a bit about 3Pi and line following, as line following is the theme of the month anyway. But I'll also refer to what I had to do for the firefighting robot. In both cases, you know, this is very much, you know, the type of robot that I usually work with. They're small, they're indoor, you know, round, differential drive, you know, being controlled by a microcontroller. You know, that's the type of robot most of the time I tinker with. You know, I don't get into the outdoor stuff, large robots, tracked robots, mecanum wheels. I haven't done any of that. And I just point that out because I'm sure some of you are going to have a question. Well, what about, how do I do this and that in simulation? I'm going to try to wing it, right, in answering the question, but I haven't used a real robot with mecanum wheels, so I can't really say how well this is going to work in simulation, right? So I haven't done certain things in simulation or on a physical robot, okay? But I have done some ROS, I have done OpenCV, right? And so any question, and you know, I've used a broad range of sensors. So again, any kinds of what if questions that come up, you know, I'll try to answer as best as I can based on, you know, what I sort of done in the past on my robots. So I mean, the end result really, you know, is something like this, and I don't know how well this is gonna work, right? So for my firefighting setup, you know, it's not gonna run at the same speed here. For my firefighting setup, I've put the simulation together that really allows me to test, you know, the heck out of my control logic. And you know what I think is in the end cool about it is that the exact same code runs in simulation and on the physical robot, right? I just want to emphasize that, because that's really kind of what I'm trying to do and explain how to do. You know, there's a lot of things you can do in simulation and just stay purely in simulation. I mean, a lot of cool things you can do. It's not so much what I'm after, right? Because at the end of the day, you know, a real robot's always going to be a lot more fun to work with than a simulated robot, right? That's kind of the reality. So the ultimate goal is to have a real robot performing its task well, okay, and to get there, you know, with less pain and less, you know, again, frustration, okay. Let me pause that again. Those videos are on YouTube. You can view them. Yeah. Pause. Okay, it's not wanting to go to the next slide. Let me try this way. There we go. So the reason I'm presenting this to you guys, right, is because, well, I mean, simulation is obviously the hot topic for you guys right now, for obvious reasons. And you know, hopefully at the end of this presentation, you have a better sense of how this works, you know, in this particular environment. And maybe you can answer some of these questions for yourself, right? Everybody's gonna have a different answer there, but you know, I want to present enough information, hopefully, in just enough detail, so you can decide if this makes sense for you and for the type of robots you're building. It may not, right? Or whether this is even, you know, easy enough for you to learn, right? That's what I want to hopefully get to, and I hope to cover enough bases here and not get lost in any particular detail, right? If I do, stop me. But I'm trying to show just, you know, enough of the pieces so you can answer those questions for yourself. Okay. There you go. All right. So when does this make sense? You know, I don't want to belabor this too long. I mean, obviously, you guys have decided it makes a lot of sense this year for obvious reasons. But even outside of a pandemic, right? I mean, you have situations where you want to run a contest. You want the folks from Seattle to participate, right, in your Dallas contest, or you have a team, right, and only one physical robot, and you want to get everybody productive, right? Maybe you have a couple people that are in a position to develop software, but you only have one physical robot. I mean, the logistics can be difficult in that kind of team setting. But you know, really, for me, it comes down to some of these other bullets here, right? When you want to, sometimes you just want to experiment with different algorithms, with new concepts. And, you know, on a real robot, that the uncertainty with the sensors and all the nitty-gritty just can get in the way, right? Let's say I wanted to actually implement a consumption-based controller, which I haven't done actually ever, even though it was the first thing I was exposed to, you know, back in college. You know, all the Rodney Brooks stuff I'm very familiar with, but for some reason I've never implemented it. Okay, so if I wanted to do that, I think I would do that in simulation, because I can just focus on the algorithm, right, and get a feeling for how it works. So if I wanted to try something with fuzzy logic, with another thing I haven't done before, you know, I think I would try that in simulation and try to get a sense for how does it work? How does my implementation even work correctly, right? So that's really kind of the main question I tend to try to answer. You know, does my code work correctly? And it's difficult to answer, right, on a real robot, because there's just so much going on. Your sensors don't always read the same value. You know, the inertia of you have so much going on that at the end, you know, you bang your head against the wall, wondering if you made a stupid mistake in your implementation, or if your logic, your thought process has some flaws, right? So I think that's where it can really help. Other practical but silly reasons for me, honestly, is, you know, you're working towards a contest, and if your arena doesn't fit in your small home office, right, how are you going to run the physical robot, right? I have a small office, multiple monitors, comfortable setup to do my software development, but I can't have the whole 10-foot by 10-foot arena in here. Okay, so it's just some logistics here. I think where simulation makes a lot of sense. Now, when, what should you not expect? When does it fall apart? Okay, this is just a couple things here, a couple very specific examples I could think of that you probably can relate to. Tuning of PID gains associated with low-level motor control. Don't try it, right? I mean, you're gonna have to spend a lot of time getting the simulation really calibrated and the dynamics taken care of and the inertias and the masses. It may not be worth the investment of time. Okay, and so I wouldn't try that. Self-balancing robots. I mean, those are tricky things. Doing that in simulation, I honestly don't know how practical that would be. I mean, I would just imagine you're gonna have to spend a lot of time making sure that the dynamics are matching your real robot. So I'm just saying in those situations where you need to fine tune some low-level gains, some sensor thresholds, that's the sort of stuff you're gonna have to do on your physical robot. Okay, that low-level stuff, get it working on your physical robot, and then in simulation, focus on the higher-level logic. Right, that's really what I'm saying here. Now, how is this different from the LFS? It's 3D. That's kind of the most obvious thing, and what that means is you're gonna be able to do some very, very basic modeling, very, very basic, and it does, these simulators, and I'll talk about a couple different ones. They do decent rendering, so that's what you get. You get a general purpose framework that's not geared towards one task, such as line following. So that's another difference. And then the main one at the end also really is it's physics-based to some degree. I mean, there's rigid body dynamics, physics engines that these different simulators are using, and that means you get collisions. I think that's the biggest one, really. You get to simulate an environment where your robot can't just drive through walls, right? And so simple stuff like that you can simulate, right? And I think that's very useful. Now, again, if it's going to be able to push some object, right? Or is it going to get stuck? Is it going to spin its wheels? Is it not going to spin its wheels? What's the exact friction? There's a lot of calibration that's necessary if you want your simulated robot to behave exactly the same way. But I think my point that I'm going to try to make at times is, well, you have to really think about what is it you care about in the end. Do you care if it behaves exactly the same way in the simulation? I would argue no, right? You have to keep coming back to, so what are you trying to achieve with the simulation, right? And again, to me, I'm trying to get my logic kinks worked out. And so if it doesn't behave exactly the same way, right? So if inertia and mass is not perfectly accounted for, maybe that's okay, right? You get all this functionality. If you really want to get into the dynamics and into the physics engines, right? You can read the user manual of the Bullet physics engine or the ODE physics engine, right? You can really dive deep into it. But I'm saying, you may not have to. You can still get a lot out of it without sort of doing that. So why am I talking about ColleliaSim specifically? I mean, it really comes down to ease of use, all right? And hopefully I'll be able to illustrate that. That's really the main thing. It's free for hobbyists, and it's in my opinion the easiest one to use of those that I have seen. Now, you probably heard about Gazebo. Why not Gazebo? I mean, I think it's much harder to use. At least I kind of didn't really get my arms around it. I couldn't really figure out very quickly how to, connect my own code to the simulator. The user interface is just a bit more challenging. I think it's also a little bit more sluggish. That said, if you're deep into ROS and fully kind of bought into that ecosystem, that may be the tool you want to learn, because all the examples in ROS, are using Gazebo. It's kind of the de facto simulator in ROS. Now, that's not to say that ColleliaSim can't work with ROS. It definitely can. and but if you're doing RAWs, and if you have to choose, how to spend your time and what tool to learn, I'm just saying you may want to look at that. Now it has a steeper learning curve, unfortunately. And last but not least, another noteworthy one here is VBots, and it's much easier to use than Gazebo. I think it's still a little harder to use than ColleliaSim. It's actually one that I came across many years ago when I first tried to decide which one to use. That one was on the list of things I looked at. Back then, it wasn't free. Okay, it turns out last year they open sourced it. Okay, so that used to be available only to, universities, and even that not free of charge. So now this one's fully open source. It is promising. So again, if you want to really get into this and trying to decide which tool to learn, I do encourage you to kind of look at those three and kind of make up your own mind, because this one is promising. It's got a couple of cool features. It's got even a little IDE built in. Not really necessary, but it's got some cool features, especially when it comes to things like simulating sensors and sensor noise. Some of that is built right into the simulator, versus in ColleliaSim, yeah, you got to write 3 lines of code sort of separately to simulate sensor noise, right? Not a big deal, but they have things in VBots that I think are cool. Like with cameras, you can turn on simulated motion blur, for example. Okay, ColleliaSim doesn't have that particular feature. I think that would be very important if you're doing a lot with vision, right? Your robot's moving, and you're gonna get a motion blurred image, right? So this tool actually would give you a motion blurred image in the simulation. Okay, so that's just a brief overview of what's out there and why I've chosen ColleliaSim. Before I start to dig deeper, any questions?
How about a big wow? Because that looks like a really comprehensive
yeah, it's
review.
cool. While you were talking, I downloaded the educational version, and I have a line follower up and running. Very interesting. I guess I want to know more. I'm really interested in okay, so now I want to program the thing. Make sure we talk about that. Okay.
Yeah, we will. So, okay. There's really 4 things you need to, in the end, you need to learn if you want to do that. And, you need to know how to use the simulator. We'll get into that. You need to, again, and the context here is running the same code on the simulator as well as the physical robot. So keep that in mind, right? So you need to also learn or know how to correctly structure your code so that you can do that without too much pain, right? You obviously need to know how to interface your code with the simulator, right? So that goes to your question there, Ron. And then you need to know how to calibrate things, and including your own expectations, because again, it's all models are wrong, right? Some are useful, and that's the same for simulation. In the end, you want to keep asking yourself, how well does it have to reflect reality in order for it to be useful to you? Okay, because it's very easy to get go down some rabbit hole and trying to make it work perfectly like your real robot. It's not worth it, right? You have to stay focused on what are you trying to achieve. And again, to me, it comes back to productivity. All right, so how to use the simulator. So just a couple basics here on the slide before we open up the simulator itself. Basically, the way you build a robot, or the environment for that matter, is you put building blocks together, right? And there's a number of building blocks that ColleliaSim gives you. Out of those, the first 4 here really cover almost everything you need to do. Okay, you have shapes, you have simulated motors, they call it joint. You have a generic proximity sensor that gives you distance, and you got a vision sensor that you would use for a camera, and we'll have some more details here. With those 4 things, you can, that's, again, that is really 90% of what you would find yourself doing if you're using this tool. And it really comes down to, you put these pieces together. You're following a particular set of guidelines, and then you adjust the properties of each of those building blocks, right? Properties like geometry, obviously, you know, size and so on, position, obvious things, appearance. There's a lot you can do with appearance, and I should say I'm not even gonna get into that because I haven't, since I'm not sort of trained in CAD modeling and creating a mesh, you know, I'm not even ever trying to really make my simulated robot look, you know, correctly. But there are workflows you can employ here that the documentation will tell you how to do. If you have a mesh file that's of the right format, right, from a 3D CAD software, you can import that, and you'll get a 3D representation of some real robot that's very good looking, right? That's entirely optional, right? So there's a lot of stuff you can do with appearance. In the end, it has nothing to do with what the simulation does. It's really all just, you know, making it look pretty. Dynamics, every object here has some properties that deal with dynamics. Again, things like mass and inertia. And then visibility, you know, you can configure things, whether some object is visible to a certain type of sensor, right? That's what I mean by visibility. There's all kinds of settings there that allow you to basically determine, you know, how certain sensors interact with certain objects. Because sometimes you want to just say, you know what, I don't want this sensor to see this, right? Let's just pretend this isn't there, right? So there are convenient ways basically to, I don't quote unquote cheat, right? By picking sort of settings there. You know, when it comes to shapes, for example, and we'll see that when I open it up, sometimes you just want to put a few cubes and cylinders together to sort of build a little, you know, structure here representing the base of your robot. And you want to take shortcuts, you know, you kind of, you know, if you have let's say a circular base, right? Like this guy here, circular base. Now you can see where the wheel is. The wheel is not outside the circle. You see that, right? It's kind of in the circle. All right, well, the shortcuts they give you in ColleliaSim is you basically simulate this as a, you know, a disk for the base and then a disk for the wheel, obviously. But those two objects will intersect each other, and we'll see that. But you can say, you know what? Let's just pretend my simulated wheel does not interfere with my simulated base. Yes, they occupy the same space, right? One goes through the other, kind of. But you can tell the simulator, you know what? Those two things just don't interfere, period, right? So that's what I mean by these properties. And then every type of object will have its own object-specific properties. You know, when you get into the sensors, there'll be field of view, minimum and maximum range, those kind of settings that you'll have to adjust, right, to match something, to match this generic proximity sensor to your actual whatever you're using. Okay. Now, here's some concrete examples. I mean, this is, again, you can build a lot of robots with some of the items that I show here. For your wheels and your base, well, you use a combination of cylinders and cuboid kind of things, and you bolt them together. Motors with encoders, or not, or no encoders, either way. That's called a joint, a revolute joint. Again, there are settings there. You tell it, yeah, I want to just be able to continuously revolve that joint. A servo motor, right? That's also a joint, right? But there's different operating modes, so you would choose the position control mode there, and you tell it to go to a specific position, right? So that, you know, becomes your servo basically. Your sharp IR distance sensor there that most of you probably used. Well, okay, so that's a generic proximity sensor. You'll have to play with the you know, a min and max range settings. Again, these sharps are notorious for they have a minimum sensing range. You can't be closer than X, to the sensor. But that is something you can, again, you can control here with this generic sensor building block. It's got numerous parameters that allow you to control, again, the field of view, the range, and so forth. Ultrasonic sensors, again, they have their own unique characteristics, which is if you're bouncing off of an object at some angle greater than X, guess what? You're not going to get the echo, right? It just bounces off the wall. And unless, if you're facing the wall perpendicular, you get a perfect reflection. Once you're beyond, let's say, 30 degrees or whatever the angle is, right, you don't get the echo anymore. Okay, guess what? You can tell that generic sensor building block, don't provide a reading if the ray, the virtual ray that's coming out of the sensor impacts the object at an angle greater than X, right? So there you go. So that's the most important thing for modeling, proximity sensors like this. Line following sensors like this QTR sensor array from Pololu, and in the, I don't have that exact array on my 3Pi, but just individual sensors there. Well, you end up using vision sensors as the building block. And, vision sensors, think of it as a camera, but the way you're using it here is we're not interested in an image. We're not getting an image here. So you make this a 4 pixel by 4 pixel simulated camera, but then all you're asking for is the average intensity value. You don't care about an image, right? Really, what you want from this vision sensor building block in the end is, the average intensity. Okay, so that's how you turn what otherwise would be a full-blown camera, you turn it into a line sensor, right? RGB sensors, again, similar. There's other kinds of light intensity sensors, RGB color sensors. You would use the vision sensor as a building block and tweak the parameters so that it matches the characteristics more or less, right? And then you'd use the appropriate API to get to just that information that you cared about. Again, it's a simulated camera. You don't care so much about the actual image in terms of a bitmap, right? You just care about some RGB information and the ways to extract that from this simulated camera. Now it gets a little more sophisticated, right? So, okay, so what about a sensor that just picks up flames, right? A very specific spectrum of UV or IR, right? So on my firefighting robot, you'll often run into these situations. You have a very specific sensor that does very well in the situation that you need it for. Okay, well, now you're going to have to resort to probably some additional logic around the sensor, right? Because, for example, these flame sensors, right, they won't pick up any ambient light, right? That's why you're using them. Unless you're in like direct sunlight, this guy on top left won't pick up anything. They just pick up, let's say, the candle, in my case, right, from my use case. So how do you do that? Well, again, what you end up having to do is for something like this Hamamatsu in particular, which as soon as you're in the right space, in the same space of a flame, it gives you a positive reading, right? So to simulate that, you just have to take a shortcut. For example, such as, knowing that you're in the space that the candle is in, and just you simulate that signal. You have special code in place that kicks in just in simulation, just to sort of say, yeah, I see the candle, it's in this room, right? Just so your code can continue executing and so you can test out everything else, right? You don't necessarily, in simulation, what I'm suggesting is you don't want to or should try to, simulate the nuances of a sensor like that. It's just going to be too painful, right? And the gain, there's just not that much gain there, right? But you need enough functionality sometimes just to keep your robot going, right? And so again, that's where, occasionally some special hacks and special logic will have to come into the picture so that you can just say, oh yeah, I see that, all right, or I hear the sound, right? ColleliaSim doesn't do anything with sound, right? So you're just gonna have to have some special, code that's part of your glue code, right? To say, yep, I hear the sound. It's getting picked up by this microphone. All right, so and simulate that piece of information. LiDARs, they're nothing more than a proximity sensor with a very focused ray sitting on a motor, okay, and spinning around. That's how you simulate that, and they have it ready to go. Gyros, IMU, that kind of stuff. They have building blocks that give you that. But inside of it is really nothing more than one of the other fundamental building blocks plus some scripting that's attached to it, and we'll talk about that in a second. Now it gets even harder, right? And some of you are using the OpenMV, right, in bottom left here. How do you represent the OpenMV in ColleliaSim? Well, the answer is, well, it gets hard, right? You'd have to maybe use a regular vision sensor, add some OpenCV code to it that implements the same kind of functionality that the OpenMV implements, right? And maybe that's all you care about. Again, you don't want to get hung up on, or you can't afford to really get hung up on all the nuances of that specific turnkey, sensor appliance. You want to focus on what actionable information comes out of it, right? The way you're using it, maybe it gives you a bounding box around some yellow object, okay? Yeah, you may have to sort of re-implement that in OpenCV just so you can, again, exercise the full scope of your controller logic end to end, right? There's no magic here that I can think of other than doing a little bit of legwork, trying to implement the same thing in OpenCV. Hopefully it matches what the OpenMV is doing close enough, just so that you can, again, exercise your whole controller logic end to end in a closed loop fashion, right? That's really, again, to me, always the goal. There's always sort of individual things that you could easily get hung up on in trying to accurately simulate, but maybe you don't have to get hung up, right? Maybe you just sort of wing it in some cases, right? So that you can exercise all of your code. I mean, because remember, this is not going to replace running your real robot, right? Running your real code with your real robot on the ground and seeing how it behaves. It's not going to fully replace that, right? And your real sensors in the real world, they're going to behave a certain way. You're still going to have a real good feeling how they behave, right? And fine-tune a few things in the real world. It's unavoidable. If you're building a real robot, you're going to run it in the real world, and you're going to tweak things. But if it's a complicated mission that your robot's trying to implement and you're using sophisticated algorithms and stuff is just not working, sometimes it doesn't matter, right? If your simulated vision sensor is delivering the exact same characteristics as your real vision sensor. That's really my point, okay? All right, so let me open up this thing. Well, I have it open, so we put it up here. Okay, so I mean, some of you apparently have already installed it and run it. When you open it and when you get sort of this empty world here, and I just want to sort of walk you through a few of the most important concepts here in the user interface. Again, my claim is this is very easy to use, right? I'm trying to convince you this is actually something you can learn. It doesn't have a huge learning curve, right? Again, sometimes things are just too much for us to absorb, right? There's only so much time we have. But I think this, as you'll see, this is reasonable, okay? So you have a bunch of sort of things on the toolbar on the left, and you've got your toolbar on the top here. And this scene hierarchy is kind of the most important thing you're going to be working with. Every object is sort of represented here in this tree, and you see out of the box it kind of populates a bunch of weird stuff here, right? What it really is it gives you a floor, okay? It's apparently resizable. It gives you some lights, and you can't always see those, but that's what you know, you can manipulate those lights. Again, that was one of the basic building blocks I told you about. Most of the time you're not going to touch it or spend much time with it, but you know, for those of you who want to get really into it, you know, you can tweak how the lighting comes together in the simulated environment. I find myself not really touching it much, but there's a lot of options.
Are you saying that this thing does ray tracing and shadowing and things like that?
So a couple years ago, when I was really into it and spent a lot of time on it, it was not doing that. Now, this latest version, I honestly am not 100% sure if they have gotten to that. Again, and this is one of those areas where VBots might have a leg up. And I have only spent like half an hour in VBots after installing it, so I'm not 100% sure either. They're certainly going to show shadows. Let me put it that way. At least in VBots, in the rendering, shadows are visible. I'm not sure to what extent the sensors are picking it up, right, in terms of different lighting. So I have to dig in more. But I had exactly the same question, and I had for my firefighting robot, one of the tough things that I couldn't properly represent in simulation is the candle flame. The candle is usually near a wall. The walls are white. The walls reflect the light from the candle. Confuse the heck out of your sensor. I couldn't find a way to do that in here back then. Maybe they can now. I couldn't find a way to do it. So again, in the end, you know what? That's just something you test the heck out of it on your real robot, and your simulated robot is still going to go through all the motions of finding the candle and, you know, zooming in on the candle. It's just not going to get confused by the reflections. Okay, I just, there was no way to do it back then. So, but good question. I mean, it's something I'm curious about myself. Have they implemented sort of some ray tracing kind of functionality? So there's lighting going on, and there are cameras in here. So what's happening right now is you're looking at the world and everything in it through one of the cameras, okay? And they have a bunch of cameras that they just populate all over the place, and you can't see them right now. But if you click up here, there's a couple other predefined views. And what's really happening here is it's just a split screen. And now we end up looking through things through different cameras. Again, there's cameras, not to be confused with vision sensors. Cameras are just there for us humans to kind of get a particular view of the world, right? And you can zoom in here, you can move stuff around, and you know, you can't quite see the effect of it because I have nothing much going on yet. But that's what these cameras are. You get one that's just looking down from the top, one that's looking from the front, one that's looking from the side. It's just very useful when you're putting something together. You get top view, side view, front view, right, in here. So that's what this stuff is in the screen that you get out of the box. The floor, some lights, and a bunch of cameras, okay? Now, remember how I said, you know, you're going to put things together from building blocks, right? And those building blocks are here, okay? Shapes. We talked about shapes. Those are just really, again, I said very, very simple 3D modeling. Don't be sort of expecting a lot of sophisticated 3D stuff here, but you put things together out of these shapes, right? And then you see how all the properties are accessible through these dialog boxes. And again, to me at least, that's why I found this a bit more approachable than some of the others I found in Gazebo and even in VBots. Just getting to these properties and tweaking them and seeing what happens, I just, you know, I didn't find it as user-friendly. right? Let's say you wanted to change the geometry of this. So this is 10 centimeters diameter by 5 millimeters. Boom, there we go. There's your circular base for your robot, okay? Right there, done. Again, this is not visually very appealing, okay? But it is all that sort of the simulator in the end cares about. Because even if you do get more into the depth of what you can do from a visualization point of view, and I won't have the time to get into that and attach a mesh to it, that's all just for us to look at and make it pretty. The simulator wouldn't care about it. And what I mean by that is, if you look at this floor thing here, well, what is this floor thing? Well, it's a rectangular surface of some sort, okay? We don't see it actually. What we see is this mesh, and you can see there's a different icon there. What we see is this mesh, and that has a certain texture to it, right? I can clear it. I won't do that now. But that's what we see. The thing is, the simulation doesn't, I should say, the physics engine doesn't see that. All the physics engine sees is what's kind of underneath this texture, right? Now, the vision sensors, etc., they see the texture and everything. But from the physics engine's point of view, it's important to understand that there are things that it doesn't care about, right? And there are things that it does care about, such as primitive shapes. So this is where all the sort of primitive building blocks are, so the shapes. Again, we talked about a camera, not to be confused with vision sensor, different types of lights. And then really sort of, like I said earlier, the proximity sensors and the vision sensors, right, is ultimately what you're going to spend the bulk of the time with, right? So let me sort of kind of fast forward, 15 minutes or so into what does it look like when you put a couple of cylinders and other objects together into a 3-pi, right? I'm not going to go through the full motions of it because it would take a little bit of time. So I'm just going to, like I said, fast forward a little. And if you look at this simulated 3-pi here, right? What are we actually looking at? Well, we're just looking at, sorry if I'm moving around a little bit here. We're just looking at a cylinder, right? At a disk. That's the base. Nothing more to it. It has certain dimensions, right? That's it. It has certain thickness, certain diameter. You try to match it. You go in there. Geometry dialog. So what we're dealing with here, 95 millimeters, and then 2 millimeters thick. That's my base. Okay. So then attached to this base are a number of other things. And again, that's where this is an important concept here, kind of this hierarchy that you're seeing, right? You have always some parent object and child objects. And when things go together and are part of one thing, you gotta follow that hierarchy. And that's an important thing to remember. So attached to my base are now 2 motors, okay? We talked about joints earlier. So I have a left motor represented as a joint and a right motor represented as a joint, okay? So if you zoom in here, actually the size of it, in terms of how it's rendered, is actually very much irrelevant. At the end of the day, just kind of the fact that it needs to be centered or located in a certain place, that's all that matters. Again, the blue and the orange is really just for us to see, and you can make it look a little bit like the real motor. But all that matters is that this motor is attached to my base, as represented by this hierarchy, and it's in a specific location. And attached to the motor is another disc. It's a wheel, right? Again, very important. That's kind of always the order of things. You got your base, you attach the motor to it, you attach the wheel to the base. that's how it has to look in the end. And I talked earlier about sort of some of the important shortcuts that you have to take sometimes, right? You see how my base is sort of this 95 millimeter cylinder in the bottom, and then my wheels, they are 32 millimeter diameter by 7 millimeters. You see how the wheel just goes magically through my base? That's fine in the end, because I told it that the wheel shall not interfere with the base. Again, and that's what makes your life very easy, right? Because you wouldn't want to have to accurately model this base now with the exact shape that's cut off. It would just get too complicated, right, and time consuming. But this is one of those time saving things where you can just say, you know what, I have to remember where that is now. If I open up the wheel. Okay, so if I open up the wheel and we get into some of the properties that are associated with the dynamics, things like inertia and mass. You see up here this concept of respondable. Well, that's just another word for things that can interfere with each other. And what I have basically told it here is this wheel is gonna interfere with everything else in the world. So that's the so-called global respondable mask. But on this robot, on this parent, it's only going to interfere with other objects that have this checkbox checked here. And then if you look at the robot base, same dialog box, I just clicked on the robot base, you see how the different checkboxes are checked? Okay, that's to say that, okay, this thing won't interfere. That's basically how you say, well, these two things, even though they occupy the same space, they're not going to interfere with one another, right? So that's where there are certainly things like that that are not immediately obvious, that are not going to jump out at you right away if you start playing and tinkering with this tool. So you are going to have to look at the documentation a little bit and follow through some of the tutorials where they point that out, right? Again, because otherwise that wouldn't be obvious, and what would happen if you don't do this? The robot would just fall apart. I mean, it literally, the physics engine is going to get, totally confused, and it's just going to break things apart. Right? But you tell it, nah, you don't interfere with one another. So great time saver. So you see how, something as simple as this 3 pi, right? You really just have, what, 1, 2, 3, 4, 5 objects here. You got the 5 line sensors here, and you got a caster wheel. And there's different ways you can attach a caster to a base. What's typically recommended is you do it through a force sensor. Again, you can't just sort of put the caster there. It has to know that it's attached to the base, right? And that's just kind of one way you tell the physics engine this caster, which is a sphere, right? This sphere is attached through this force sensor to the robot base, right? That's what I'm telling it here, and that's how the physics engine wants it, and that's how it will sort of do the right thing in simulation. Okay. Oh, you can actually see something interesting here. My z coordinates here are such that I'm actually below the floor. As soon as I start the simulation, it'll probably jump up. Boom, you see how it jumped up, right? So that's, again, kind of irrelevant. We are sort of in a state right now where the simulator is not running. And so things like this that interfere with one another, it doesn't care about. But the moment I start running the simulation, it cares about the fact that this wheel is embedded in the floor. Well, that can't be. So it just kind of pushes the whole robot up. Boom. Right?
So it looks like it pushes it up, and then it uses gravity to hold them together.
Exactly. So gravity is simulated here, but the reason the floor doesn't fall, into the abyss is, and that's another important concept here. The floor was told, hey, you are not a dynamic object. Physics does not apply to you. Okay, in terms of, by physics, I mean in this case mainly gravity. That's what this body is dynamic means, and that's another one of these important concepts that comes into play here. Sometimes, and they call it, the language they use, they call this a static object versus a dynamic object, because the physics engine doesn't really get involved here. Now, things are still colliding or interfering with the floor, right? This is what this respondable concept is all about, right? I mean, my wheels, and you see all the checkboxes are checked, which means every other object in my simulated world here is gonna interact with the floor, right? I don't want things to sink into the floor, so the interference has to be there, but I don't want gravity to act on the floor, right? Because if I do that, watch what's going to happen. Okay? Everything is falling into the abyss, right? So again, this is just how you tell the physics engine what you're trying to do here, right? You want the floor is solid, it doesn't go anywhere, but things can't just sink into the floor. That's what we're telling it here. Okay? You see how, I mean, I'll open up a wheel. Okay, another thing that is important to sort of tweak, kind of a little bit part of calibration, is material. Okay, so again, this is just, I haven't applied any texture to this, and you can make it a little bit prettier by applying a texture. But one thing here is this material dialog box that is important, because you do want to usually say that the wheel has a fair amount of friction, right? I mean, it's a rubber wheel, so it will have a fair amount of friction, and that's kind of the only parameter in this. This just gets down into the weeds of the physics engines. Honestly, I don't care about any of these parameters. I don't know what they mean except for friction, because that's really all you care about, and only because you're dealing with wheels, right? And so different physics engines have their own set of parameters, and I'll talk a little bit about the different engines. But one of those things you end up having to do to match your real robot is you're going to have to crank up usually the friction here. And I forgot if one is the default, or what was the default. And again, I'm not trying to be totally accurate here. I just don't want to be in a situation where my simulated robot has the wheels spinning, right, just for no apparent reason, right? I don't want wheel slippage in my simulated robot. I actually don't want the wheels to slip, so I would make these parameters large values. And again, there's other documentation that tells you what the units are, etc. I don't want to get into that, but the only thing you have to remember is you look at the friction of your wheels. Okay, important. Mass. What you'll find, what they recommend in the documentation is that the physics engines, they tend to struggle a little bit if the masses are too small. Okay, so they get there can be oscillations that can be unstable if the masses are too small. And again, I haven't really dug into the physics engines and how they work, right? I'm just trying to make use of them here. And so what they tell you is, if you get very strange results, increase the mass of your robot or individual objects, right? Until it kind of behaves the way you think it should behave. Okay, so that's one thing to keep in mind here. Now again, if you really want precise, reproduction of your physical robot, you're gonna spend a lot of time here tweaking these masses and the inertias and really reading up on the physics engine, right, to find out, how to accurately represent your physical robot. But what I'm suggesting is, it may not be what you're really after, right? At least I'm not usually after very, very accurate, reproduction of my physical robot's dynamics, because it's hard. Okay, I want accurate enough so that I can run through all my code and it more or less, behaves the same way. That's all, right? as it is in the real world, there's so many corner cases that, you know, there's sensor noise. You know, there's limited gain to be had from trying to be too perfect here, right? That's really my point. The line sensors, okay, so on my simulated 3Pi here, the 3Pi has 5 line sensors, these QTR sensors, and I think I've got the positions correct here. Yeah, what are they? Well, they are vision sensors, like I showed earlier. There are, well, cameras. You may call them a camera, which not to be confused with the camera in ColleliaSim. But what I'm doing here is, okay, this is just a 2 pixel by 2 pixel vision sensor here, okay? Some minimum and maximum range, very limited range. And this is this is orthogonal. This is not a perspective angle. So this doesn't have a field of view. This is just more like, think of it as a, you know, there is no field of view concept here. It's not, you know, it's not a perspective angle. I don't know how to explain it, but it's just, it looks straight down, right? And this is kind of how wide that field of view is for that vision sensor. And then that space gets mapped onto a 2 pixel by 2 pixel image, okay? Now, like I said earlier, I don't really care about the image here. And when we look at the API that's used to talk to this, you'll see that, you know, I'm not actually retrieving the image, right? Luckily, there's an API that lets me just get the average intensity value, right? Because ultimately, that's what we're looking for, right? You know, the average intensity value, if you're a little bit half on white, half on black, right, you're going to get some 50% value or something, and that's all you're after in simulating something like a line sensor. Nothing more, nothing less. Now, if we had a robot here with a real camera, right, yeah, then these settings would be different. We would be using some real resolution here. We would have some real field of view kind of the camera configured here and all that, okay? So,
is there a reason for it being 2 by 2 versus 1 by 1 or 3 by 3?
Yeah, I think for something like a simulated line sensor, you wouldn't want 1 by 1 because most likely it's gonna go from white to black instantaneously, right? Whereas a real-world sensor, if it's somewhere right on the line, on the edge, a real-world sensor is going to give you a 50% or so reading, right? And in order to achieve that, you need some number of pixels here. Some of them are going to be on the white. Some of the pixels are going to be on the black, right? Then you ask for the average intensity. You're going to get that, and so that's just, you know, that way it behaves more or less like your real line sensor. Single pixel is just not going to give you that transition. That's, you know, smooth transition from black to white and black and back to black. Okay. So we covered the robot bases, the base, the line sensors, the caster wheel. Again, caster wheel, we talked about friction earlier. Well, that's one thing you want to make sure, you know, you reduce the friction coefficient for that, right? You don't want that to sort of really slow you down. You want the caster wheel material to be configured for something that's very, very low friction, because usually that's what you end up using. And we don't care about simulating something that's even rolling on the floor. I don't care. You know, the real 3Pi obviously has a little wheel, a ball here that rolls around. I don't care, right? I don't need to simulate that. I just need a contact point with the ground that's of very low friction. That's all, right?
Yeah, I mean, already, even in the physical world, right, the thing about that 3Pi caster wheel is it has friction and inertia, but we ignore it in the real world because it's so small.
Yeah, exactly.
Unless you make a beer felling robot for a contest in AT&T, and then you have this big old tail and has drag, and then it actually becomes an issue. But the 3Pi one, it's got no inertia, no friction. Who cares? That's why Dave is smiling, because we did it wrong for a bit. Yeah.
All right. So let me. So any questions? So I want to cover enough breadth. So I don't want to cover the simulator in depth, but any basic questions to help your understanding of the simulator. Let me just think any other UI features. Okay, one important UI feature I just want to mention is here. Again, a lot of things you can't see. Things are get placed into layers. I mean, layers is not a difficult concept, but certain things that you don't usually care about are in some layer that's usually not visible. And by playing around with this, you can actually make specific layers visible or not visible. Let me just turn some of these off.
Oh, can you import an image? Can you import an image? Let's say an image of the DPRG line following course.
Yeah, you can. Okay, and when you do that, this is what you get. So what I've done here.
Okay, that's it. I'm taking LFS down off GitHub. I don't want to waste any space.
No. So what I've done here is I've put the floor together, and ignore that name here, 525. It's I've put a floor together, and my understanding is the physical footprint of this is what is it, 5 by 7 feet, right?
Yeah, that's
pretty close.
Yeah. So that's what I've done. I created the floor 5 by 7 feet, and then I've gone in here again. Here's the floor. I've removed the texture that comes with it by default. And what I've done is I have simply applied a texture to it. Okay? I made the floor just white and then applied a texture to it. And I don't know where I have it now, so I'm just going to do an undo here. But that's it. It has there are different ways you can apply a texture. Luckily, it is smart enough to figure out, the aspect ratio of the image that I have here that was given, right, matches exactly the aspect ratio of my floor. So it works out okay. I mean, it does a weird thing here. The texture technically wraps around. It's probably on the other side as well, but we don't really care about that. You get exactly what you kind of want. And I mean, that is the quickest way actually to do line following. That being said, they do have actually features in here for creating what they call a path, right? That lets you sort of specify the coordinates right in here, and then you can visualize a path in different ways. But not really a big advantage to doing it that way, and it makes just much more sense, treating this as a texture applied to the floor.
Okay. Chris, how do you then make how come is it by default the sensors are now aware of that texture?
Yes. So again, I don't know how to answer sort of the ray tracing question, but everything you see here, right, is unless you somehow turn it off by accident or on purpose, is visible to your senses. All right. There are, again, things you can do to sort of change that. Sometimes you don't want to see certain things. All right. Again, I'm looking at a sort of drop-down box here, where you can say, hey, this is a specialized vision sensor. It only sees the candle, nothing else, right? Well, you have a way of doing that in here, but usually you say, yeah, I want to see everything that's in the scene, okay? And your floor, and therefore the texture that goes with it. Again, there's a concept of camera visibility layers. There's just a couple ways by which you can control what a given sensor can see. But again, unless you specifically turn it off, right, the texture gets picked up by the vision sensor.
Gotcha. Thank you.
Okay. In fact, if I go here, again, I just switched to the layout that's like perspective view, top-down view, what's that? Front view right here, side view right here, obstructed by the cylinder. Let's get rid of that. It's a convenient way to do the editing because you get this kind of different views of it. But if I hit the run button here, I just want to point that out because now these things here are what's called floating views. And a floating view can be told to display either a camera, and again, cameras are just for us humans to look at stuff, or they can be told to pick up a vision sensor, right? And that's what I've done here. I've told these floating views to show me what these vision sensors are seeing, right? Unfortunately, it only shows you when you're sort of running, all right? Okay, I paused it right there. So these floating views here show me what my vision sensor is seeing, and it's just one way to sort of give you a little bit of a user interface and a little bit visibility into what's going on with your sensors and with your robot. The other thing that kind of goes hand in hand with that would be what they call a graph, and the graph object itself, you don't really care where it is. The point is, we've talked about that, on the call, the real-time, real-time graphing of your data. Well, my point is, with this graph object, you can actually do that. And again, it's going to take a little bit of time to do it here, but this is just one of those things that they give you to actually help you visualize your data. Okay. Now, what just happened is I added it while the simulation was running, and the way this works is as soon as you stop the simulation, everything goes back to normal, right? So you can be doing stuff while you're in simulation. I can move the robot around. Okay. And I don't know why it went back just now, but whatever I do in simulation, as the moment I hit stop, everything goes back to the way it was before, which is usually the behavior you want, right? So that you don't inadvertently make changes to your stuff while you're sort of, investigating things while in simulation. Now, before we get into sort of more of the code behind this, sort of any other questions about the simulation? Let me see what else I forgot to mention here. Oh yeah, model browser. So in addition to the basic building blocks, right, they give you kind of, composite building blocks, for lack of a better word, right? So they give you things that are put together out of the primitive building blocks, things like a LiDAR, okay? And they try to give you a selection here of things that represent real LiDARs. If what you've got is a little different, you're gonna have to tweak things, right? They give you here the simulated Kinect. And of course, there is a 3D mesh here. That's why the Kinect looks like a real Kinect, right? Behind the scenes is just two vision sensors, right? That's all there is. One in depth mode and one in RGB mode. But they have put a mesh around it so that it actually looks like a real Kinect. But in this model browser here, in this library, they give you all kinds of objects. You want to, if your robot lives in a house, you can have furniture, right? That sort of thing. People, office items. And then what they call tools, for example. There's a couple things in there, and unfortunately they buried it in tools. There is a way to single step, and I don't know where it is right now. There is a distance measurement tool. Sometimes you put stuff together and you're not really sure, well, how far it is from here to there, and you can use this tool, and you can measure things sort of ad hoc in here, just to sort of confirm that some of the stuff you are doing here in your 3D model actually is, as per real world dimensions, and so, etc. Right? So this model browser, there's a lot of sophisticated stuff in here that again, I don't really want to get into here. There is certainly, you know, my use of this tool, I'm just scratching the surface, right? I mean, that should be clear by now. There is so much you can do, and so many different types of robots you can simulate that I'm not going to have the time to get into, right? I focus on simple, small, indoor robots and how to program those more quickly. But there is a lot more you can do if you want to invest the time to learn the tool, you know, by all means. That's kind of the takeaway here. But again, I don't want this to look too overwhelming, right? My point really is, hey, look, yes, a tool like this is going to have a learning curve, but you know what? It is not that hard to sort of get your arms around this, right? You just work, you read some of the documentation, you just put your robot together with these primitives, you adjust some settings here. Yes, you're gonna have to refer back to documentation once in a while for sure, but out of the million features in here, right, I'm using 10. So, and you can do useful stuff with that, is my point.
Yeah,
Okay.
I see one shortcoming. Maybe there's a way around it. They only allow you a 2K by 2K pixel texture. And right now, at least to do the LFS, I'm using 10K by 5K pixels. So maybe there's a way to solve that. But if you decided you want to dump LFS, you'll have to solve that problem if you want to do whatever, the same resolution, let's say 64 dots to the inch. So maybe there's a way to fix that. I don't know.
Yeah, the way I would do it, I guess, is to just not worry about the resolution and the dots per inch, right? I mean, the aspect ratio of the image has to match. If it does, and if your floor here is the correct real-world size, the texture mapping just does the right thing, right? And the lines will be the right width. Yes, you're gonna technically lose some resolution, right? I mean, if you were to zoom in on a line, you'd probably find it getting a little blurry because the texture you imported, you know, was low resolution. That's what would happen, right? You'd have a less crisp of a boundary here between black and white. That's all. Now,
well, that's a little tricky, though. I mean, when you look at some of the fine features in our contest course, at least, but you know, you can always do a little piece of it at a time. There's always that option.
Yeah. Now, since you're talking shortcomings, and I think I forgot to mention it earlier, that the one thing that, you know, you do give up is speed, right? I mean, this is gonna run much slower than the LFS, that's for sure. Don't even think about getting 5x real time here in simulation. You know, once you have a couple pieces here, sensors and motors, it's just not gonna run 5x real time, okay? Especially once you connect it to your controller code, you know, and the two are communicating, that slows things down a little bit. So if you're getting 1x real time on your computer, you're doing good, right? So that's, again, just to set expectations. When you're strictly in this environment without your controller code talking to it, yeah, you can get 2x real time probably if you don't render every frame, and if you don't run at 50 hertz or 100 hertz. So you can get 2x real time, maybe 3x, you know, depending on the parameters. But having your code talking to the simulator does slow things down. So it's again, don't expect more than real time here.
Can I make a comment and a question then? And the comment is that Ron, I think by no means should we even use the word or the phrase dump LFS.
I was just being whatever, facetious.
No. It seems to me that's very clear that is the target. At the very least, for the contest, we're going to use LFS.
No, I'm just taking a critical look here because, yeah, I think it's a great tool, powerful tool. And certainly in my past dealing with dynamic simulations, I'm sure this is pretty wicked in some of the things it does. So anyway, okay, I'll shut up.
Pros and cons. No, I think they're both cool, but for their own purposes, right? And it seems clear to me.
Sure.
So, and then that leads to the last thing, Chris, the question of, I think you'd mentioned earlier on having a part in here where you were going to talk about how to connect the simulator to your own controller code. Is that coming up?
Yes.
Okay.
Okay.
Nope.
Ah, read your mind.
Well, yeah. So how to connect it to your code is part of it, but also how to structure your code. The two are a little bit related. So I'll try to get through this in time. Do we have a hard stop? Because I know we're coming up on 2 hours here. How much time?
The recording can go as long as you want.
Give me an upper limit.
Does anybody have a hard stop where they need to bail?
Keep going.
Nope.
This is great.
You got us hooked, Chris.
All right, good. So we'll get into the code. Now, some of this, naturally is going to depend on your circumstances, right? Circumstances such as, well, you already have a ton of existing code that you need to reuse, and you're trying to figure out what to do with it, or are you starting from scratch on a new project, right? That's going to influence things a little bit. Also, are you mainly working in C, C++? Are you working on a microcontroller, right? Or are you running Python on a Raspberry Pi, right? Again, some of the details will depend based on the answers here. Now, again, in my situation, the answer would be, okay, I'm usually using C, and it runs on my physical robot has a microcontroller, and so I'm dealing with C code that, at the end of the day, has to run on the microcontroller. But again, the concepts, I think, are universal, just the details, differ. Now, so to make this all work with the least amount of pain, there's a couple best practices, you have to follow. And some of this, I think David Anderson has pointed out in the past. I remember, him presenting various talks on software. And so some of this is all known. It's just more of a reminder. There's certain ways you can do this that makes, in the end, your life easier. And number one is, you really want to try hard to separate your logic, from everything else. And everything else is all the low-level stuff, anything that has to do with I/O, anything that has to do with, that's specific to your physical robot. You want to keep those things separate, both structurally, meaning, separate source code files, but then also when things are executing. We'll talk about that a little bit. So instead of mixing everything together, right, you want to have a clear separation of I/O and logic. And what that means in the end, again, unless you have constraints that we can get into later, is you want your code to be structured so where you're reading all your inputs, all of them, right? And then you run your logic, and your logic assumes that one way or the other, all the sensor values have been obtained. The logic doesn't care how and where everything comes from. The logic just has the information accessible, okay? The logic produces outputs, usually motor speeds, okay? You don't want the logic to directly, manipulate the motors. Instead, those outputs go somewhere, and when we're all done running through an iteration of our logic, right, you actually apply the outputs to where they need to go. Again, mainly motors here. And then last but not least, you don't want to do this just as fast as possible. You want to do it at a specific rate that you have decided to do it at, and you want to control that rate. You want to know what that is. Again, because otherwise, again, it's all about, in the end, making sure that the code that you have that runs on your microcontroller behaves more or less the same when you run it on some different types of computer that also is running your simulator, okay? So that's really what I'm trying to say. If you structure it this way, you're making your life a lot easier. Now, what does that mean? It means, and most of us won't do this, you wouldn't want to access directly some, register on the microcontroller to control the PWM duty cycle. Now, I think usually we don't do that. Usually we use some API that was given to us, right? In my case, Pololu, right, is what I often use for platform, right? So you use some API, you tell the motors what speed to go, or some value between 0 and 255. Now, like I said here, preferably you don't even do that in your logic. Again, preferably preferably your logic is even detached, from specific APIs. Why? Because it just makes your life a little harder getting that to run on some other computer, right? Preferably, your logic just takes some inputs that come from somewhere and produces some outputs, okay? So again, if you're starting from scratch with a new project, that's what I would encourage you sort of do. And, again, whether it's C or Python, the concept's the same. Keep your controller logic separate from stuff that I call platform specific. Now, if we can get into situations where this is not always practical, but here's just an example of what I mean by what to avoid, in my opinion. And this is verbatim the Pololu example for their simple line following, right? It's an Arduino project, so you got this loop going on here. Okay, right away you can say, I don't know how fast this loop runs. It runs as fast as possible, and you don't want that. You need a more explicit management of time, and then it calls these APIs. This is very simple code, so it's not that the code is bad, that you get lost in it. It's just that if you want a piece of code that runs on the Pololu 3Pi, as well as on the Windows in my case, or if you're a Linux user, ColleliaSim runs on Linux as well. This code, without some other magic, right, isn't going to run on Windows. I don't have these APIs, right? So now, if you're in a situation where you have too much code that's using such APIs, right, you may say, you know what, I can't just throw all that code away. And so, so what I have done in the past, and I did that on my firefighting robot, you may have to go as far as creating kind of a stub, for some of these APIs. That would be the approach, right? If you want that same code to run on Windows, well, you're gonna have to keep your compiler happy and the linker happy. You're gonna have to let it include files that are called the same way, and you're gonna have to have at least a straw man of a orangutan motors class that implements at least one API, and that's called set speeds. In the end, actually, it's very, very little code to do that. But again, if you're starting from scratch and you have a choice on how you approach things, you can avoid that kind of situation of having to write, a straw man implementation of these APIs, so that on the Windows, you can do this. Again, it is often necessary. I have found myself having to do that. Again, it's not as bad as it looks. If you find yourself in the situation, just to illustrate here, right? This get milliseconds API that the Pololu library gives me on my real robot. Well, okay, guess what? On Windows, I've implemented it. It returns a value, and the value comes from a data structure where I kind of maintain what I consider the model of the robot. So that in my code, where I've sprinkled this API occasionally in for various reasons, I can freely call that API, and I will know that on the Windows, because of the way the plumbing works behind the scenes, I actually get the correct time. Again, I'm not saying you want to do this. I'm saying you should avoid having to do this by structuring your code so that your logic is 100% separated from any platform-specific APIs. Okay, so that's practice number one. Number two, I would say, you should avoid sort of sophisticated preemptive multitasking inside your logic. I'm not saying it doesn't have a place. I mean, you may need some multitasking to interface with certain sophisticated sensors, but I'm saying in your logic, if you're going to have multiple tasks running sort of in pseudo-parallel, that's going to make life more complicated, right? Because now how do you get that same piece of code execute the same way on your microcontroller as on your development host? I mean, that may not even be possible, and if it is, it's going to be a ton of work. But if you stay away from having multiple tasks at at your controller layer, you're really making your life easier. So again, what I'm saying is, in this layer here, in this layer here, where you're just trying to do the decision making, you know, don't split that into multiple tasks that somehow work together. Now, that said, multiple tasks can keep your code very, very clean, or I should say much cleaner. So the way around it is, you know, instead of using a preemptive multitasking, use cooperative multitasking and use state machines. And I've used both. And the reason cooperative multitasking is not as problematic is because it's not something very low level. It doesn't manipulate the stack pointer. It's not like some real task switching is going on. It's fairly straightforward C code, and I got my setup from this cocoos.net website. And it's C code. It's doing a little bit of NCC magic. Again, my perspective is C and C++. And it'll work on a microcontroller. It works on Linux. It works on Windows. It's really not creating real tasks. It's just letting you write code that makes it look like your tasks. And so it keeps your code very clean, but everything is actually just one single task, and we're bouncing around between these different functions. State machines is the other thing that I use a lot. Again, sometimes state machines, you know, things get a little convoluted if you have like, okay, do this in this state, wait for a second, then do something else, wait for a second, do something else. Well, now that's 3 states, right? Kind of your code gets a little bloated. So, you know, a combination of state machines and cooperative multitasking is what I found most useful. Then, most importantly, you know, is you have to watch out how you're managing time and how you're keeping track of time, because you don't want to be in a situation where you have code that now asks the operating system, you know, okay, how much time has elapsed since last time we've been here? Because it's just gonna behave very differently on the real robot and on your host, right? You want the simulation to be in charge of time. And so you basically, again, you can call APIs that Linux gives you or Python gives you, and you're asking for the current time. That time is going to keep on running, right? If you're pausing the simulation, you want time to stop progressing, right? You're pausing things. You want to be able to pause everything. I mean, that's kind of the power of this, right? You want to be able to pause things and look at things and continue, run it more slowly, okay, speed up again. So nowhere in your code can you afford to sort of, you know, you make some assumptions about time, right? It has to come one way or the other from the simulator, and we'll get into that blue code in a second here, okay? So those, again, ideally you follow some of these practices. You know, there may be some things, some reasons why you have to bend the rules a little bit, but I would say this makes life a lot easier in terms of just not just, right? Because there are 2 pieces. There is the getting your code to talk to the simulator piece, and then there is the, you know, actually being able to run your code on a different computer piece, right? Getting your code to run on the simulator, you know, talk to the simulator piece becomes a lot easier if you have this sort of seemingly low-tech, you know, super loop here, read inputs, run logic, write outputs. But it becomes easy because, you know, when you're in simulation mode, guess what? The way you read the inputs is done one way. The way you write the outputs is done another way. And the way you progress time is, well, you tell the simulator to step 1 step further, right? On the real robot, you're just changing the code that implements this loop, right? But number 2 here, run logic, you want that to be identical, right? That's where often sort of the hard stuff is. Now, again, that's not to say that working with sensors and the motors and all the low-level stuff is easy, right? You kind of have to work all the kinks out on your real robot with your encoders and low-level motor control. working all the kinks out of that, you do that on the robot, right? So maybe what I didn't mention earlier is, right, I'm kind of assuming that you have worked some of the low-level kinks out, right? And now you're moving on to, working on the algorithm, working on the logic, on the control logic, and trying to sort of decide exactly what to do there, okay? And that's why it's so important that so helpful if it's separated in this fashion, okay? So I think we covered this slide. All right, so let's look at some of this, and how to interface this. Before I pull up code, any questions on what I've just said in the last 10 minutes? Okay.
Hey, just one observation. Just taking a quick peek at your Cocoa OS, I think it looks a lot like Mr. Anderson's LMK, which he wrote, I don't know how long ago, but.
I think his LMK is, I don't know if that's cooperative multitasking or actually something more sophisticated. No? Okay. Yeah, the one thing about, and I haven't looked at LMK, but is the LMK involving any assembly code or just strictly C code?
There are bits of assembly in there. Oh, David.
It's a cooperative multitasker. There's about 5 lines of assembly.
Okay. Yeah, so the Cocoa OS, and, I forgot what the actual feature is called that you're using in C. It has to do with some trickery with the switch statement and some, and basically there's no assembly involved. It all just strictly C code, and it gives you the appearance of cooperative multitasking. It has its own caveats. I won't have time to get into that. Maybe I'll touch on it at some other time. But for me, again, the important thing was, I can just take this. It compiles on my Pololu platform. It compiles on Windows. Great, with some tweaks. Oh, and by the way, it uses minimum RAM, which I don't have much of, on those Atmel AVR micros. And by the way, it never disables interrupts. And that was another concern for me on my firefighting robot. I got a ton of stuff going on there, pumping a lot of data in and out wirelessly over Bluetooth, interrupts firing every 100 microseconds. And I didn't want to miss any of that. So I wanted something that's never ever gonna disable interrupts on me so that I don't miss any data coming in on the Bluetooth link or so there's a couple. That's some of the reasons. Again, it's the main concept to remember is, again, you want to do something that's portable. That's really the bottom line. It has to be portable between whatever computer you're using on your real robot, and then whatever you're using to run the simulation with. It's going to be either Windows or Linux, of course, right? So as long as it's portable, and as long as things from a timing perspective behave the same way, and by that I mean, I don't care if things take a microsecond on my Windows laptop and a millisecond on my Atmel AVR, but in terms of sequencing, right, you have to be able to say in the end, my code runs in the exact same order, or all pieces of my code run in the exact same sequence, right? And that's why I'm saying preemptive multitasking is gonna make it challenging to achieve that, to say the least. All right, so in terms of code now, to put all this together and sort of end up with the simulated 3-pi going down, following the line, what I'm showing here is this control, this robot logic, okay, the one piece I was talking about earlier, which is very simple, a very simple line following logic. I'm not going to discuss the merits of the logic. It's very simple. It's basically the way the Pololu sensor array works. It gives you a value of 2000 if you're right on top of the line, and then 0 if you're too far on one side, and 4000 if you're too far on the other side, okay? So that comes back from that sensor array, and I'll show you how I produce that. in simulation, and then there are the 5 individual line sensors. So all I'm doing here is I'm just saying, well, are we too far to the left or are we too far to the right? I'm going to steer by an amount that's proportional to my error, okay? If we don't see the line, you know what? I don't know what to do. I'm just going to go straight, okay? And you know what? If we're steering, let's also slow down at the same time a little bit, is what this line is doing. And then, okay, now I know what I want to do with my motors. You know, I'm going to adjust my nominal speed by some steering amount and by some speed adjustment. Again, I don't want to debate the merits of this logic. It's very simple. The point is, okay, this modular C code here has absolute zero dependencies to anything else in the world. Okay, it is completely standalone. It doesn't care, right, where information comes from. But obviously, as you probably have seen here, I'm accessing some data structures here. Okay, and what I have here is, and this is obviously going to be specific to your situation, all the inputs that my controller cares about, I put them into some simple data structure, right? All the outputs that I'm producing in my controller code, I stick them keep them together in a structure here just to keep things clean. Yeah, and then I just put all of that together into a structure that I call controller state. You know, it includes the inputs, includes the outputs, and then includes stuff that's neither an input nor an output. Okay, like how much time has elapsed. Okay, so now what you'll be asking yourself is, okay, where does all this come from, right? And now, obviously, what happens now when I run this on the real robot, this structure gets populated somehow, right? And this elapsed milliseconds comes from somewhere. And on the simulated robot, you know what? We're just going to populate the structure differently, and we're going to do something different with this output. But the key here is this is 100% portable C code. It does not use any other API. And if it was using some math function, you know, that would be fine. But it's not using any Pololu API. Right? I'm running this on the Pololu 3Pi. But in this piece of code, right, if I want to like play around with different control logic here, this is where I would be doing it. I wouldn't be calling any Pololu API here. Okay. Now, any questions so far? So that's what the logic looks like, or an example of logic. I mean, this is not even using any state machine here. This is sort of as simple as it gets. Right? So now how to glue this together, okay? How to attach this to the simulator. So what you can see here, this is in Visual Studio. Just you see the structure here, and I showed you the GitHub link. But in my Visual Studio project here, again, I have the controller logic here at the top level. And then I have this subfolder here called Simulator Interface, okay? So that's where I've put all the glue code, right? There's 2 pieces to that glue code. One is a couple C files that just come straight from ColleliaSim, and I call it VREP here because that's what they used to be called, okay? That's the old name. So that's in this folder, and I'm not going to even open it because that's code that they provide to you. It just has to be linked in with your controller. That's all. Think of it as a library. It's just, you know, I'm just compiling those C functions in here directly, okay? So it doesn't really matter what this is doing exactly, except what it does really is it implements, you know, one of those APIs that you can use to talk to the simulator. And there's a handful of ways to talk to the simulator, but the keyword to remember here, you know, if you want to do something like this, the keyword to remember is my robot controller is a remote API client, okay? There's half a dozen other ways to do it. More specifically, I guess I'm using the legacy remote API is kind of the keyword, right? If you want to know, you know, if you're digging into documentation and you're wondering where to find some of the stuff I'm talking about, well, what I've decided to use is what they now call the legacy remote API. You know, 5 years ago, that was just called remote API. And that's what's implemented in this subfolder. The thing I want to look at is that you have to worry about is, okay, the actual glue code, right? Code that's using the ColleliaSim API and that's populating sort of the structure that I just showed you earlier. And there's just a small number of pieces to it, right? Some of it is generic, some of it is specific to your robot, but actually you can see here, let's show this first, because that kind of gives you the 10,000 foot level overview. So when I'm running in simulation, my entry point, right, is here actually. It doesn't have to be in this file, but that's where I've put it, right? When I'm running on Windows, this is what's running. And what is this doing? Very simple. It's calling an init function, and then it's going through the loop here. I'm, advancing the simulation by one step. I'm, accessing the simulated sensors. Then I run my controller logic. Okay, that same code that I showed you earlier, this exact same function, just compiled here and running on Windows. Then I'm gonna access the simulated motors, do a little bit of statistics display, and the cycle repeats. Okay. Again, it's conceptually the same thing as what's going on right in the LFS and any other simulator really. But again, the key is to have your controller code structured such that you can do this, right? Because in simulation, this is what I'm doing to get the inputs, and this is what I'm calling to get the outputs. And this code should not care about it, like I said, right? So how do we get the inputs and the outputs? Well, let's look at the initialization. This is very generic here, so someone could reuse this as is. And it's calling this SimX functions. Again, this is the so-called legacy remote API, very well documented. Not a lot you need to know here other than, you got to start. You got to establish a connection with the simulator. Maybe you want to stop it in case you left it running. Then the next point is important, though. I'm putting it into synchronous mode because I don't want the simulator to just run at its own pace. I want my simulator and my controller code to be in lockstep. Right? That's important. Otherwise, I can't really synchronize the two. Okay. Then I'm starting the simulation, and then comes a little bit of robot-specific stuff. You know what? I need to get some identifiers so that I can access the simulated sensors. So we'll look at that in a second. That's kind of robot-specific. And then that's it. And then I sort of advance the simulation by the first step just to get things going. And that's it. Now I have a connection to the simulator, right? And now what I can do, right? Now what I can do when it's time to get the simulated inputs, right? So now it gets a little bit more interesting in terms of glue, how this is all glued together. Now I'm getting my simulated inputs. Now this is somewhat robot specific, right? This wouldn't be generic code anymore. But the very first thing here is I'm asking the simulator what time it's at, right? Are we 100 milliseconds into the simulation, or where are we exactly? And then sort of I'm keeping track of that here. Okay. In fact, yeah. So and then I have other functions here. I'm actually pretending to have encoders on my 3Pi. We can look at that too, but how you simulate encoders. But really, most importantly, I'm accessing the simulated line sensors, right? And what your code for your types of sensors would look very similar, right? And I've just split it up into separate functions so that this is a little bit more readable. But if you look at the simulated line sensor and what I'm doing there, right, as I mentioned earlier, it's implemented as a vision sensor. And so all I'm doing here is I'm using this API to read that sensor. Now I'm not reading the image, okay? There's another API for that. I'm just reading metadata. And it so happens that they provide, a couple pieces of metadata information. One of them happens to be the average intensity of the image. So I don't even care if this is a 2x2 vision sensor or a 16x16. This code doesn't care, because the simulator gives me the average intensity, and that's all I care about, right? Now, I'm getting that. It's a number from 0 to 1. Again, that's the sort of thing you'll find in the documentation. All right, then I'm simulating a little bit of noise, okay, just to keep things real. Again, this is where you end up adding a little bit of your own code, right, to do that. And then in the end, I'm just making sure that my simulated line sensor, matches up with the, with the definition of black and white, compared to the Pololu, sensors. So this is more of a helper function, because then what I'm really doing it, I'm mapping this value here from 0 to 1 to a value between 0 and 1000, because that's what happens on the Pololu platform, right? So that's where you have to sort of now, this is not calibration per se, this is just mapping of ranges coming from the simulator into the range of values that your code is familiar with, right? Now, you could step this up a notch and kind of make sure your code works, in engineering units that make sense, rather than arbitrary units here, and for a line sensor, I'm not sure what that would be. But again, maybe you have code that's just works directly with the range of values that the Pololu API gives you. You know what? That's okay. You can probably do better than that, but you're not necessarily violating sort of my practice or rule number 1. But I gotta get the simulated sensor into that same range, and that's what I'm doing here. And then what I'm also doing here is the Pololu API includes one function called read line, and it kind of spits out a number that's getting calculated for the 5 individual sensors. So I'm kind of replicating that here, okay? They kind of take all the 5 individual sensor values. You can see what they're doing here. I'm doing the same thing that the Pololu code is doing. I've decided it makes more sense for me to just replicate that simple logic rather than try to pull in the Pololu implementation and run it on Windows. Not worth my while. It's a very simple logic that's going on inside the Pololu function, and I'm kind of replicating that here, so that by the time I'm done with this function here, there are 6 outputs coming out, 5 representing the individual line sensors, right, that I'm pumping into my structure here, and then a 6th output which represents what the Pololu readline function would give me. So this is kind of some of the key glue code, right? Again, you're calling simulator provided APIs to get simulated sensor readings. You add some noise to it. You map it into the range that you need it to be at. And then the last step is you stick it into this, just as a global variable that's the structure, basically, right? Because that's what my robot controller expects, and it doesn't care how the values got there. It just expects them to be there. That's all. Now, you may ask, some sensors update very slowly. What do I do? Like my ultrasonic sensors, you can't just ping them arbitrarily fast, right? If you have multiple of them, you got to alternate. So this is sort of the place where you would find yourself, doing a little bit more logic here, depending on the sensor. I have an ultrasonic sensor. If you say you can fire it only once every 20 milliseconds, and you're running through this once every 10 milliseconds, you know what? You're just gonna have to skip, every other step here, and that way you effectively replicate the slow update rate of an ultrasonic sensor. Same with the sharp IR sensors. They don't update really once every 10 milliseconds, not even 30. I think the spec says, sorry, not even 20 milliseconds. The spec says 30. You know what? To sort of simulate that on the conservative side, you can just say, you know what? I'm reading the simulated sensor, but I'm not going to propagate the value, at every iteration. Okay. and you only propagate that value once every other iteration, once every third iteration, and so on, right? Because, I mean, it is important, right? Again, you don't want to go crazy in mimicking the real world, but you do want to be close enough for this to be useful, and that doesn't mean, you know, getting some noise in here. It doesn't mean, you know, replicating a very slow update rate of certain sensors, okay? So that's how we get the inputs. And then, I mean, there's a corresponding function for the outputs. In my case, that's obviously very trivial. I don't have a lot of outputs to deal with. I have 2 motors to deal with that are identified here by these file handles, left motor, right motor. And here you can see again, I'm mapping the values that come back from my robot controller code, you know, which works in units that make sense for my robot, and I'm mapping that into units that make sense for the simulator. And I don't have this calibrated too well. This is very approximate, and I did a bunch of math and a bunch of measurements that I talked about the other day, and it just roughly works out to that. I need to divide the number by 4. Good enough, right? It probably needs a little bit more calibration, but this is what you would end up doing here with your motors, right? You would have enough calibration going on here. Maybe you have even a lookup table of some sort going on here, right? You can do a number of things, you know, to take the value coming from your controller logic, right? That value is in here, state.out.left motor, right? That value needs to get mapped to what's equivalent in the simulator. The simulator wants rads per second. You know, in the GUI, it operates in degrees per second, but the API operates in rads per second, right? Again, all that's documented. And so you do that sort of mapping with your, you know, with your actuators, with your joints, with your motors, right? And then, right? And then everything loops around. You carry out the next step, which is obviously even more straightforward. The next step here is nothing more than, okay, let's call the API that actually, you know, tells the simulator to go to the next step. Now here's really where I'm actually getting the time from the simulator. I have some duplicate code in here, but you see that's where I'm getting the time from the simulator, and I'm sticking it into my state structure. Again, very important. My robot controller code has no notion of time other than what I tell it, you know, through this structure. My robot code doesn't call any APIs to find out what time it is or how much time has elapsed. You know, everything works off of this elapsed millisecond, you know, variable. Now, again, in this particular controller code, we don't actually use time, but if I had logic that depended on time, right, this is what it's based on. It's not real time, calendar time. It's simulated time that I obtain in this fashion. Now, there's a few other things you can do now. You can have a user interface, sort of like in here. You guys in the LFS, you talk special keys to make the simulator do certain things, and then this is the same concept in here. You know, I'm looking for keystrokes. You know, the space bar, it makes I go into slow motion mode. Some of this leftover from my line, you know, from my firefighting code is I can make the robot movable so that the simulator doesn't get confused. I can drag it around then with the mouse, that sort of thing. What I've done in the past also here is, you know, in the simulation, I have a special key that I press if I want to know exactly, if I want to pretend that I have 100% accurate encoders, right, and motor control, I can just obtain the robot's position from the simulator and say, you know what, I'm just going to ask exactly where my robot is. I'm going to feed that back as input into my controller code rather than having it calculate odometry or ignore odometry. So that's just the sort of thing you can do here, right? You can just ask to an API, you know, and I was doing that up here, get object position, right? Where is the robot? get object orientation. Well, what's its orientation? Okay, I keep obtaining that information, and so if I wanted to use that, ground truth, right, I could. That's kind of my point here. So this is kind of, again, so there's not that much glue code here because, well, it is a very simple robot, a very simple problem, the line following, but that's kind of to give you a flavor of what that glue code looks like, right? It's, again, just a matter of using the right APIs to access your proximity sensor, manipulating the values a little, and then taking the output from your controller and shoving it back into the simulation. Now, before I show you what that looks like on the real robot, or let me actually show you, let's make sure this actually runs, right? Or am I just sort of cheating here? Let's see if this works. I don't care about real time. Let it go as fast as you can. So let's see if this works still, or if I've messed it up in the process. Or start without debugging. Is it doing something or not? Okay. Oh wow, why is this so slow? Wow, what the heck?
Presenting on Google Hangouts.
It's okay, so now it's going. Okay, I didn't even tell it to go slow motion. It decided to on its own. Wow. Yeah, I don't know if it's running in super.
So how fast would it run normally, you think, without being on Google Hangout?
Yeah, I don't know. So, and it's not going to get very far, trust me. Maybe if I'm lucky, it's not going to get lost. But this is the simple logic that I just showed you, very trivial, just looking at the center of the line is. And ordinarily, this does run much, much faster. I don't know why this is getting stuck. It must have to do with Google Meets. Of course, as soon as we get to this here, it's, see how it's just going straight? And we just get lucky and hit the line again. And this one, we're probably going to miss. Okay, we got lucky. We just caught the line again. You know what happened? It actually did better after I added simulated noise. Most of the time, it's catching that line there. So I get real lucky, and that's why I asked earlier, okay, what did the rules say about this? So this is what it looks like. Again, performance is usually a little better than this. There's something weird going on right now. But you can have, if I hit the space bar here, now I'm going slow motion and so forth. To me, the real cool thing now, honestly, is, okay, I said run without debugging. I can run this in the debugger, okay? And if you're in a situation where you are banging your head against the wall, okay, I don't know if I have any breakpoint here. Oh, okay, I did. All right, I have a breakpoint here. Okay. Oh, well, we're in the middle of the controller logic here. Okay. So what's it telling us? We're at minus 2000. That means the line is to one extreme. We'll calculate a steering angle here. Oh, steering is 0. Okay, because we're not picking up anything yet for some reason. And so, well, we're just going to go straight. Let's run the next iteration here. Nothing yet here. Okay, so now we start to pick up sensor values. And so, if I was banging my head against the wall, why it's not catching the line or something, right? Then I would resort to this and step through the code, right, and see what's going on. Right now I'm paused, and so this is paused here. I can zoom in here, right? I can see, okay, so where am I? What okay, I'm here. I'm pretty much centered on the line here, okay, subject to some noise coming from the sensors. I should be I should be seeing a value here that represents, center, more or less, right? And so, again, in some situations, this single stepping kind of can be very beneficial, in my opinion. All right. So let me stop that and just show you what that now looks like. Okay. What that same code looks like on the real robot. All right. Now, for that, I open this up in Arduino. I actually have the way of doing that in Visual Studio, just more convenient for me. But basically, just to keep things simple, I've taken the Pololu provided simple line following demo, right? And it's Arduino, which I don't do that much in. So it's got the setup function, and it's got, this is all Pololu provided code. It's interacting with the LCD. Again, like I said earlier, all these APIs, I wouldn't want those anywhere near my controller logic, right? I don't care about any of this stuff. I want to keep it away from my controller logic. But this is all part of setup, the real 3Pi, as you guys, or some of you know, right? It puts stuff on the LCD here and so on, and it beeps a little bit. All of that stuff we don't care about. In fact, there's another thing I don't care about. It's important on the real robot. It's doing a calibration step as part of the setup here. You know what? I've chosen not to replicate that in simulation. You know why? Because in simulation, I can say, I'm getting perfect white, I'm getting perfect black, in the range of 0 to 1,000. I don't have to exercise this calibration logic on my simulated robot. It's just more glue code to write, right? More work to do for little in return. And so that's the sort of thing you have to keep reminding yourself of, right? I mean, what is it I'm really after, right? All I care is that at the end of this calibration that happens in the real robot, it's going to give me numbers between 0 and 1,000, regardless of the exact color of my floor. That's important, right? And so, but that's, in the end, I'm getting a number between 0 and 1,000. That's all that matters. All right, and so it's waiting for me to press a button before I get going. Again, I don't care about any of that in simulation. And this is the original Pololu logic that I had a screenshot of earlier in the presentation, right? It's going through that loop as fast as I can. I've just left it here, commented it out, and you remember that function in the vrep.c? Well, this is kind of the corresponding function on the real robot. We are running through a loop here, but what we're doing now, instead of obtaining simulated sensor values, is a couple things. First, again, we find out exactly what time it is. Now, in this code here, right, again, this is not my robot controller code. This is glue code, right, intended for execution on the real robot only, right? This is not meant to be portable code here. This is just a wrapper around my core controller logic. In this wrapper, I'm allowed to do what I need to do. I need to call some APIs to find out what time it is. I need to call some APIs to read the line sensors, right? And once I call this API, it's going to populate this array. It's going to give me this number, right? It looks familiar, right? I'm taking those values, sticking them into this data structure, okay? Then I run my controller logic, and then I take the output of that and again call some Pololu specific API. The answer is yes, you can play with this code. It's all in GitHub, and I just did a commit before the meeting to make sure everything's in there, including the.
I didn't realize you were reading the comments, Chris. So I feel bad because I've been writing some stupid comments anyway.
No, I didn't see all of them. This one just caught my eye.
He caught me. Oh, gee, I feel so busted. Oh, gee, okay, shutting up.
So again, I deliberately kept this simple, right? On my firefighting robot, there would be a lot more going on, and it would just, you get a little bit lost here in the mess, and it's not as clean. So I created this 3Pi example just recently from scratch, A, because I wanted to use my 3Pi, and B, because it just, it makes it a little easier to explain the concept on a simpler example. But I mean, this is really the key. Again, there is an element of, discipline here that's necessary to keep things separate. That's, again, the key concept here. Keep your robot controller code separate, and then you can do all kinds of things like this, right? Now, again, if you're starting out with a lot of existing code, what are you to do, right? That's where certainly it sometimes takes a bit of refactoring to get everything into a shape, and structure that lends itself to this type of approach, right? So it doesn't come for free. It does take some work, but at the end of the day, I found that it does save me time in the long run, and I'm able to fine tune my firefighting logic, which is a lot of corner cases and a lot of specialized logic I put in place to deal with different corner cases, and just a lot of code written late at night, right? And guess what happens? It's just a lot of bugs in there. So I think, yeah. So I think I want to pause here and open it up for questions. I probably didn't touch on all the important points that I wanted to touch on, but I don't want to go crazy over time. So let me sort of pause here and open it up for questions. And the GitHub link is already in the chat. I pasted it in just before I started, so it's there.
Okay, cool. I think really anybody that's listened to this probably needs to play with your demo, I would think. There we go. Oh, that's nice. Great.
Chris, that's phenomenal. I mean, that is over the top what you pulled together. And I mean, we've had a lot of talks about simulation in club. I know several of us have done it, but the way that you've gone through this is so clean, and I'm in awe. Thank you very much.
Yeah.
Well, thank you for having me. We all like to share, so
Very good.
sharing. And again, I will come back to be realistic. This is not for everybody or for every situation, right? Because it does take some investment of time. Again, like I said earlier, I think this particular simulator is easy enough to learn, so that you don't spend 6 months just learning that, right? So, but then again, the big investment of time may or may not be in you having to restructure your code, right? It kind of depends on where you're at, with what kind of code you have, what kinds of sensors you have. Like, are you dealing Array with his OpenMV camera? Again, I didn't have like a real good way of saying, this is how you deal with that. It's the simpler the robot, right? Obviously, the easier this is to do, right? That's obvious. And but even if the robot's sophisticated, again, you just have to ask yourself the question, all right, what do I want to get out of this? And for me, it keeps coming back to, I want to execute my code, with feedback going on, end to end. I want to run through all the logic, right, without the robot being down on the floor and me having to pick it up. I want to be able to step through the logic. I want to be able to find stupid mistakes that I make in the code, right? And then when all those kinks are worked out, guess what? I mean, there's still a few things that need to be tuned on the physical robot, right? Thresholds, any kind of motor control, PID loops. You got to tune those things on the real robot. Don't plan on tuning those in simulation. It just would be a lot more time consuming.
Chris, I really like, especially though, how you showed how to abstract and structure the code. Because I know I've struggled a lot in the last few years, not having done this professionally, and just trying to figure stuff out on my own. But I find it really, really refreshing in the way that you've got the kind of core abstract logic nicely separated from the real world. And I think it's really easy to see how, if you do that, it should make it really easy to port your fundamental logic from one platform base to another, whether it's a physical platform base or a simulator platform base.
Exactly.
And I think that's like a home run for me out of your presentation here. So thank you.
Right. But
Yeah.
again, unfortunately, what happens, right? We all start with some example code, like I did for this simple demo, right? And it's not structured the same way, right? So you, unfortunately, it's, the code you get sometimes violates sort of the rules that are laid out and the best practices, and so it takes a bit of work to get it there.
And it misleads you if you're learning, because you think, oh, this is the way it should be done, but in reality,
And I mean, I didn't show the real 3Pi running around, and I only have a small square line that I'm following, but you're just going to have to trust me that that code runs on the 3Pi and it does follow the line. Now, again, when I was running simulation, I saw weird things, and again, it comes back to calibration. I saw that it's commanding one of the motors to go backwards, right, to make that 90-degree turn. Now, when I looked at the real robot with my just naked eye, I said, oh, it's not doing that. Why is my real robot not going backwards? But then I went into slow motion again using my iPhone, did a slow motion video, and okay, yeah, the wheel is turning backwards, for, I don't know, 200 milliseconds, more or less the same amount of time as in the real robot, but probably not matching exactly, again, the dynamics in simulation. That's the key, right? You want to get close enough so that it's useful, to the type of things you're doing.
Okay, cool. Hey, can I have my response time now?
Sure.
I want equal time. No, I'm too hungry. That's really a great presentation, but I just wanted to say while you were talking, I'm jealous of that 3D stuff. So what I did is I put a 3D camera on LFS, and I'll just show you. Hang on real quick.
This is the rebuttal part of our presentation.
Yeah, here we go. So here we have
27 days from the contest, or never mind.
Okay, is it visible? There we
Yes.
go. Okay, let's fire it up. So yeah, so I took I decided I'd make that like the video camera, and then I like to have a spotlight. So that's what I did. But actually, this simulation is going to get help from LFS because this one's broken, but it does use a real video camera, and does process the images. So that's the future for LFS, and this one will run at 60 frames a second. But anyway, so I just wanted to show that off. Oh, and it does use real. The update is 10 kilohertz for a stepper-driven robot. So that's the motors are physically stepped at 10,000 hertz a second. But anyway, that's all done. So and I'll give you the flag or the function call for LFS that'll enable that later, if I'm feeling like it.
There you go. What about collisions? Can you do collisions?
Oh yeah. Well, actually, I need to scrounge up the ODE code that I wrote about 20 years ago. That's a great package. It's Russell Smith's. One guy, I think, authored one of those physics engines. He's a genius. And there are other physics engines there, but ODE, one man did. You wouldn't believe what he did. You look at his library, you'd be blown away. And I've used that with Delphi back in the early 2000s. And yeah, I'd like to bring some of that into LFS, collision and so forth, especially if doing things like can collection. Line following, it doesn't matter, just slows it down. I think what I'd like to do with LFS is bring the frame rate up. And I might be able to achieve around 500 frames a second. So we might be able to run 10x real time. So that's my goal. I like speed, and I like to get this stuff over with, so we can watch a contest run in much shorter than real time. That's my speech. I'm done. Vote for me, LFS.
Yeah, speed. The one thing about speed I found is it doesn't matter how many cores you have in your PC, because much of the work is happening sequentially, right? So what you really want for this kind of simulator to run fast, meaning ColleliaSim, you want super fast single-threaded performance.
Right.
2 cores are probably better than 1. But if you have 12 cores, it doesn't matter anymore, right? Because most of it is sequential. So you want lots of gigahertz, for this to run fast. Yeah.
Well, really, for this type of thing, the GPU is the key element. But when you're talking about dynamic simulations and things like that, unless you have GPU code to run that, then
the other thing that I found that slows it down, and I mentioned that, right? Talking to the controller code over that API slow things down quite a bit. And I haven't tried any of the other APIs to see if they are better, but you know, that plays a big role. If you're just playing with the simulator and hitting the play button and you're watching time, again, you might get to 2x real time, but once you talk to your controller code through all these APIs, it slows things way down, unfortunately.
Yeah, that's kind of why I abandoned. I was writing a client server model for LFS, and I started that out, and I sort of thought, well, it shouldn't be bad. I'm seeing about a 1 millisecond latency, but I abandoned it because it was slow, and maybe there's a way around it for sure. But within your simulator, I think that they have like a Lua scripting language. Is that run internally?
Yes, exactly. I mean, we didn't really get into that, but you know, a lot of what people do, they use the Lua scripting engine. They attach a script to certain objects. You could run the whole logic right inside ColleliaSim with Lua scripting. Sometimes, where you know, if you have sophisticated sensors like a LiDAR, you end up having to use the Lua scripting so that inside the simulator itself, you kind of end up spinning that motor, right? That holds the, you know, the laser, and you kind of building up this sophisticated sensor, you know, in your simulator. And so what you get out of it is just the laser scan, right? So again, the Lua scripting can be used in a variety of ways. So if you use one of their simulated IMUs, what they're doing is they're doing some Lua code right inside the simulator, and you know, extract the right information from the right kind of object and present it to you as if it was, you know, a gyro or an accelerometer, right? So that's where that Lua scripting comes in handy. If you wanted to do sensor noise, that would be another way to use it, right? You could simulate the sensor noise directly inside Lua in the simulator, and let it spit out another number, right? And then you access that number from your own glue code. I just like to keep things more in my own code. It's easier to version control, you know, versus stuff in the simulator. It saves this giant file. You don't really know what has changed from version to version. Unfortunately, it's a binary blob of some sort. That's why I stay away from the Lua stuff. I don't know what I've changed.
Okay, yeah, interesting. You know, I've got a few ideas, but we're running out of time here. But I've got some ideas to greatly speed that up or reduce the latency, but we'll talk about that another time. I mean, because this millisecond, you need to be running, yeah, I could see where connecting, you know, your code through an interface could be sped up dramatically. So without a question, you know, because we're talking supercomputers here, we should be able to make two things talk to each other with latencies in the microseconds or less. So anyway, another topic for another day.
I think David Anderson's having microphone things. David, you have something to say?
I was just going to ask Rob if he knows Russell Smith. Do you know Russell?
No, I don't.
I grew up across the street from him.
Oh, that's cool.
Yeah.
So my words about him being a genius, would you agree to that?
Absolutely.
Yeah.
Also a really nice guy.
Yeah, that's cool to know. Never talked to him or met him in person. Just I met his code.
Guys, I got to log off.
Yeah, me too. I think I got dinner cooking or something. Yeah. There's a chicken or something.
Thank you for
Yeah, Chris. Brilliant. You're a brilliant presenter. Wow. Better than Carl.
Very good. Thank you.
Yeah, very much appreciated. I can see. I'm never going to get to the physical robot because first I've got to challenge Ron on the line following course in his home base. And then I'm going to have to go and play with ColleliaSim, so I'll never do anything physical again ever, probably.
No, I don't think that'll be the case. Like I said, it can't be the fun, you know, tinkering with a physical robot. So it's
you're right. So that's where the credit card comes out and the stack of junk just grows, but nothing ever gets plugged in. Okay.
So a last thing, a present to myself is if I can learn how to turn my line following robot back on, my present to myself will be, and get the interface back up, is to get a full-size line following course printed. But I have to figure this out first.
Nice. Okay, guys.
All right, see ya.
Well, cool presentation. If there's nothing else, we'll see everyone next Tuesday night, and download your favorite simulation environment. Let's get going.
All right. Thanks, guys.
Thanks again. Bye.
All right, see ya. If I can find the close button. I can't find the close button. What's that, Carl?
I had to find the